Hello and welcome to Learn When You Sleep. Settle in wherever you are. Pull the blanket a little closer, let your shoulders drop, and let your breathing slow down. Tonight, we are not going anywhere in a hurry. In fact, the journey we are about to take together is the opposite of hurried. It is the slowest journey imaginable, following something across timescales so vast that every number ever spoken by a human being about everyday life becomes meaningless beside them. Tonight, we are going to follow a black hole from the moment of its violent birth, all the way to the moment of its final, quiet disappearance. And that journey, depending on the black hole we choose to follow, may last longer than a number you could ever write on a piece of paper, even if you wrote for your entire life. Take a breath. There is no rush here. The universe has already been patient for longer than we can comprehend, and tonight we will try to sit beside that patience, to feel its shape, to let it settle into the body the way warmth settles in after coming inside from the cold. The story of a black hole is, on the surface, a story about extremity. It begins with something enormous collapsing under forces no human technology could ever match. It involves gravity so strong that light itself cannot leave. It involves a boundary so absolute that physicists still argue about what it truly means. It involves temperatures and pressures and curvatures of spacetime that make the interior of the sun feel gentle by comparison. And yet, the story does not end with that extremity. It ends with something almost the opposite of it. It ends with patience, with slowness, with the quiet leaking away of energy so gradual that the word gradual does not even begin to describe it. There is something deeply philosophical in that arc, something worth sitting with before we begin the science. We tend to think of power as permanent. We tend to assume that what is vast and strong and dominant will remain so. But the universe does not work that way. The universe has its own arithmetic, and in that arithmetic, even the most powerful structures are not immune to time. Even the most absolute boundaries can be crossed, given enough of it. Even darkness, gathered into a point of infinite density, will eventually thin and fade and scatter. Not quickly, not in any sense that the word quickly has ever meant to any living thing, but eventually. And that eventually is what tonight is about. So let your mind soften. Let the walls of the room around you become less solid for a moment. Let yourself float just slightly into a perspective where the years are not counted in decades, but in powers of 10, so large they need new words. We will come back to the familiar world before the end. But for now, let's begin at the beginning, with the birth of the thing we will spend tonight watching die. Before we can follow a black hole to its end, we need to understand what it is, not as a symbol or a concept, but as a real physical structure, a place in space where the laws of physics behave in ways that challenge every intuition we have built up over a lifetime of living on a planet, under a comfortable sky, at a comfortable distance from the nearest star. To understand its death, we must first understand its life. And to understand its life, we must go back to the moment when it was born, which is always a moment of tremendous violence. Black holes do not appear gently. They do not accumulate slowly from nothing. They are forged in events that are among the most energetic in the known universe, moments when matter is compressed beyond any limit, beyond any boundary, beyond any stopping point that nature ordinarily provides. They are born from collapse, and collapse at the scale we are describing is not the kind of slow settling that the word suggests. It is sudden, catastrophic, and final in a way that very few things in the physical world are truly final. To understand that birth, we need to start even further back in the long and largely peaceful life of a star. And stars are patient things. They burn for millions or billions of years, depending on their size, fusing hydrogen into helium in their cores, releasing the energy that pushes outward against the inward pull of gravity. This balance, pressure against gravity, gravity against pressure, is what keeps a star alive. It is a negotiation that has been ongoing since the star first ignited, a steady conversation between two forces that are, for most of the star's life, roughly equal. But the conversation does not last forever. The hydrogen runs out. The star shifts to burning heavier elements, going through stages, layer by layer, building up elements in shells around its core. And each time a fuel source is exhausted, the pressure drops a little and gravity gains a little ground. For most stars, this process ends gently. A star like our Sun will swell into a red giant, shed its outer layers, and leave behind a quiet remnant called a white dwarf. No black hole, no drama beyond a certain scale. Just a slow cooling over billions of years. But for the most massive stars, the ones that begin their lives with 10, 20, 50 or more times the mass of the Sun, the ending is different. When the core of such a star has burned through its available fuel and nothing is left to push back against gravity, the collapse is almost instantaneous on any scale that matters to the star itself. The core, which may be as massive as several suns, falls inward in a fraction of a second. The outer layers of the star, still falling inward under gravity, slam into the now rigid inner core and bounce outward in an explosion we call a supernova, one of the brightest events in the universe, visible across billions of light years, releasing more energy in a few seconds than our Sun will release in its entire 10 billion-year lifetime. But at the center of that explosion, something is left behind. Something that did not explode, something that continued to collapse past every limit. Past the density of an atomic nucleus, past any boundary that ordinary matter has ever crossed, into a singularity, a point where the mathematics of general relativity describes an infinite density, an infinite curvature of space-time, a place where our equations break down and confess that they cannot tell us what is happening. Something is there. We do not know exactly what. But around it, space and time have been bent into a shape so extreme that a region of the universe is now sealed off from everything else, enclosed within a horizon from which nothing, not even light, can escape. A black hole has been born, and with its birth, the longest story in the universe has begun. A story that will not end for a time so vast that no language has comfortable words for it. Tonight, we will follow that story all the way to its conclusion, but we will take it slowly. One layer at a time, the way the universe itself unfolds, without rushing, without skipping ahead, letting each piece of the picture settle before adding the next. For now, let that image sit with you. A star that burned for millions of years, patient and steady, has in a moment of final collapse created something with no parallel in ordinary experience. A region of space where time itself bends toward a single point. Where the curvature of space-time becomes so extreme that the word extreme no longer captures it. And where, sealed within a boundary called the event horizon, the physics of the very large and the very small will eventually meet, in a quiet, slow negotiation that will last longer than anything else in the universe. That negotiation is what we are here to witness, and it begins, as all great things do, with understanding the boundary. Now that we have witnessed the birth, the collapse, the supernova, and the sealing of that first horizon, we can begin to look more carefully at what a black hole actually is. Not in the way a headline describes it, a region of space where gravity is so strong that nothing can escape, which is true but incomplete. Rather in the way a physicist would describe it, which is both stranger and more beautiful than the shorthand version. To follow a black hole across cosmic time, we need to understand its structure. And its structure begins with a concept that sounds simple, but opens into something genuinely difficult to hold in the mind: the event horizon. The event horizon is not a surface. This is the first thing to understand, and it is one of those facts that takes a moment to absorb properly. It has no material. You cannot touch it. If you were falling into a black hole and you crossed the event horizon, you would not feel a wall or a membrane or a change in temperature. You would feel nothing at the moment of crossing. The horizon is not a physical thing. It is a boundary defined purely by geometry, by the shape of spacetime in that region. It is the surface from inside which the future only points inward. It is the last address from which a letter sent outward could still escape. Cross it, and no letter you send will ever reach the outside universe again. Not because something stops it, but because outward is no longer a direction that leads away. In the curved spacetime inside the horizon, every path through space and time, every possible future, curves back toward the center. The singularity is not in front of you like a wall. It is in your future, unavoidable in the same way that tomorrow is unavoidable for someone sitting quietly in a chair. To understand why, you need to think about spacetime rather than just space. In everyday life, we think of space and time as separate things. Space is where things are. Time is when things happen. But Einstein showed us that they are not separate. They are woven together into a single fabric called spacetime. And what we experience as gravity is not a force in the traditional sense. It is the curvature of that fabric. When a massive object is present, it curves the spacetime around it. Other objects moving through that curved spacetime follow curved paths. And what we feel as the pull of gravity is simply the tendency of objects to follow the straightest possible path through a curved geometry. Near an ordinary star or planet, this curvature is gentle. The paths curve slightly, and we call that slight curving gravity. But near a black hole, the curvature becomes extreme. Near the singularity, it becomes infinite. And at the event horizon, something specific and remarkable happens to the geometry. The curvature reaches a threshold at which all future pointing directions in spacetime curve inward. Not most directions, all of them. The horizon is precisely the surface where escaping becomes geometrically impossible, not physically prevented, but geometrically ruled out, the way it is impossible to walk north from the North Pole. This is what makes the event horizon so philosophically striking. There is no guard at the door. There is no force field. There is no mechanism of imprisonment. The imprisonment is built into the geometry of space and time themselves. Once inside, you are not held captive by anything external. The structure of reality itself has reorganized so that there is nowhere to go except inward. The radius of the event horizon, for a black hole that is not rotating and has no electrical charge, is called the Schwarzschild radius. It is named after Karl Schwarzschild, a German physicist who solved Einstein's equations of general relativity in 1916, just weeks after Einstein published them, while Schwarzschild was serving on the Russian front during the First World War. He solved the equations that describe the spacetime geometry around a perfectly spherical, non-rotating mass. And the solution contained something remarkable: a radius at which the geometry became singular, a surface at which the mathematics described a horizon. Schwarzschild himself did not fully understand what this surface meant physically. He thought it might be a mathematical artifact, something that appeared in the equations but did not correspond to anything real. It took decades for physicists to understand that the horizon is real, that it can form, that objects can cross it, and that once crossed, there is no return. The Schwarzschild radius depends only on mass. The more massive the black hole, the larger the horizon. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. The entire mass of the Sun, compressed into a sphere 3 kilometers across. Our Sun is not going to become a black hole. It is not massive enough. But if it did, its event horizon would be smaller than a city. For a black hole with the mass of the Earth, the Schwarzschild radius is about 9 millimeters, less than a centimeter. The entire Earth, compressed into something the size of a marble. And for the supermassive black holes that sit at the centers of galaxies, the ones with millions or billions of solar masses, the Schwarzschild radius extends to millions or billions of kilometers, event horizons larger than the orbits of planets. What is remarkable is that the horizon for a supermassive black hole is actually a relatively gentle place. The tidal forces at the horizon of a black hole with 1 billion solar masses are weak enough that a human being could cross it without being torn apart. You would feel nothing unusual. You would look around and see the universe outside looking slightly distorted, slightly redder, slightly quieter as photons struggle to reach you from farther away. But nothing dramatic, nothing to mark the crossing. Just the quiet sealing of your future. For a stellar mass black hole, the situation is very different. The tidal forces at the horizon are immense. The difference in gravitational pull between your head and your feet, if you fell in feet first, would be strong enough to stretch you into a long, thin strand. A process physicists have charmingly named spaghettification. The same physics, the same horizon, but experienced very differently depending on the scale. This dependence on scale is one of the recurring themes in the story of black holes. What the horizon does depends on how massive the black hole is. What the evaporation timescale is depends on how massive the black hole is. Even how the final moments unfold depends entirely on the mass. So as we follow our black hole through its long life and slow death, we will need to keep returning to the question of mass, because mass is the only thing that determines how a black hole lives, how it ages, and when and how it finally ends. For now, though, let the event horizon settle in your imagination. Picture a sphere in space. Not a sphere of matter, there is no surface there, nothing to touch. Just a sphere defined by geometry, a boundary in the shape of spacetime. Everything outside it is connected to the wider universe. Light can leave, signals can be sent, futures can point outward. Everything inside it is sealed. Futures point only inward, toward the singularity that waits at the center. The horizon is the border between these two regions, and it is, as far as classical physics is concerned, absolute. Nothing that crosses inward will ever cross back out. But classical physics is not the end of the story, because classical physics does not account for quantum mechanics. And it is quantum mechanics that in the end will undo even this seemingly absolute boundary. It will do it slowly, so slowly that the word slowly does not do justice to the timescale, but it will do it. The horizon, so absolute and permanent in classical physics, will eventually dissolve. The geometry that sealed the future will gradually, imperceptibly, over timescales almost beyond description, lose its grip. And the black hole will thin and fade and finally, in a brief burst of energy, disappear. That is the story we are following. But we are not close to the end yet. We are still near the beginning. We are still at the horizon, looking in, wondering what is on the other side, what the inside of a black hole is like, what happens to things that fall in, and why the very concept of an interior raises questions that physicists are still arguing about today. So let your breath slow a little more. Let the image of the horizon float in your mind. A sphere in space, defined by geometry, sealing the future. Outside it, the universe continues. Inside it, something else entirely is happening. Let's go a little closer and look. We have paused at the horizon. We have looked at its geometry, understood that it is not a physical surface but a boundary written into the shape of spacetime itself. Now, let's ask what lies on the other side. What is the interior of a black hole like? What happens to a person, or a photon, or a clump of gas that crosses the horizon and enters the region from which there is no return? The answer is both simpler and more disturbing than most people expect, and it involves something that we rarely think about in everyday life: the nature of time itself. When we think about falling into a black hole, our instinct is to imagine falling through space. We picture ourselves moving through a region of intense gravity, being pulled inward, accelerating toward the center. And that picture is not entirely wrong, but it misses something crucial. What is really happening inside a black hole is not simply that space is pulling you in a particular direction. What is happening is that the geometry of space-time has reorganized so that the dimension we normally call time is now pointing inward. The singularity is not a place in space that you are moving toward. It is a moment in time that you are moving toward, and you cannot stop moving through time. You can no more resist the singularity once inside the horizon than you can resist tomorrow. This is one of the most genuinely strange things in all of physics, and it takes a moment to let it settle. In ordinary space-time, there are 3 dimensions of space and 1 dimension of time. You can move freely through space in any direction. You can go left or right, forward or back, up or down. But time you cannot choose. You move through it in one direction only, from past to future, without any ability to reverse or pause. Inside a black hole, the singularity has effectively taken the role that the future plays in ordinary space-time. It is not in front of you in the spatial sense. It is ahead of you in the temporal sense. It is your unavoidable future, built into the geometry. This means that an observer falling into a black hole experiences something unusual. From their point of view, they are simply falling. They feel tidal forces, stronger for smaller black holes, as we discussed. They see the universe outside distorted, compressed, shifted toward the blue as they fall, and then toward the red at the horizon. But they do not experience anything like hitting a wall or entering a special region marked with warning signs. They simply fall inward, and the singularity comes to meet them, not from a direction, but from the future. How long does it take to reach the singularity? For a stellar mass black hole, the fall from horizon to singularity takes only microseconds. The black hole is so small and the gradient of space-time so steep that the journey is almost instant. For a supermassive black hole with 1 billion solar masses, the journey could take hours. You would have time to look around, to see the distorted image of the universe gradually compressed into a shrinking circle behind you, to wonder about what the equations are not telling you. But eventually, for every infalling observer, the singularity arrives. And at the singularity, our equations fail. The singularity is the place where general relativity predicts infinite density, infinite curvature. The equations reach a point where they return infinity as an answer. And in physics, infinity as an answer to a physical quantity is almost always a sign that the theory being used is incomplete, that something is missing. Physicists generally believe that the true nature of what happens at the singularity requires a theory that combines general relativity, which governs the very large, with quantum mechanics, which governs the very small. We do not yet have a complete theory that does this. String theory, loop quantum gravity, and other approaches are attempts to build one, but none has been confirmed experimentally. The singularity remains, in an important sense, a mystery. the place where our best tools of understanding reach their limit and confess inadequacy. But here is the interesting thing. For the story of the slow death of a black hole, the singularity is not where the most important physics happens. The most important physics happens at the horizon. Because it is at the horizon, that invisible boundary in spacetime, where quantum mechanics finally gets involved. And it is that involvement, so gentle as to be almost undetectable for most of a black hole's life, that eventually undoes everything. To understand why, we need to think about the space just outside the event horizon, not inside, where the classical description of spacetime dominates, but outside, in the region just beyond the horizon, where the curvature of spacetime is intense but still finite, still describable, still within the range of our equations. And we need to think about what quantum mechanics tells us about that region. Because quantum mechanics tells us something very surprising about empty space. It tells us that empty space is not empty. It is never truly empty. And the closer you get to the horizon of a black hole, the more dramatically that non-emptiness becomes relevant. This is where the story pivots. This is where the seemingly permanent and absolute event horizon develops its fatal flaw. Not through any mechanism of classical physics, not through any force or pressure or material process, but through the fundamental nature of the quantum vacuum, the quantum structure of what we call nothingness. And to understand that, we need to spend a little time thinking about what quantum mechanics says the vacuum really is. In classical physics, empty space is simple. If you remove all matter and energy from a region of space, you get nothing, a void, a true emptiness. The vacuum in classical physics is defined by the absence of everything. But in quantum mechanics, this picture breaks down entirely. The vacuum is not empty. It is a seething, fluctuating medium filled with what physicists call virtual particles, pairs of particles and antiparticles that pop into existence for brief moments and then annihilate back into nothing. They are called virtual not because they are imaginary, but because they are not directly observable in the way that real particles are. They are fluctuations of quantum fields, brief disturbances in the underlying fabric of reality that appear and disappear so quickly that they are not detectable as individual events, but their effects are measurable. They affect the energy levels of atoms. They produce forces between objects placed very close together, an effect called the Casimir effect that has been measured in laboratory experiments. The quantum vacuum is real, and it is not empty. Now place this seething quantum vacuum near the event horizon of a black hole. The geometry of spacetime near the horizon is extreme. The curvature is intense. And this intense curvature of spacetime has an effect on the quantum vacuum that is unlike anything that happens in flat, ordinary spacetime. The curvature disturbs the vacuum, stirs its fluctuations, separates what would ordinarily stay together. And the result, worked out mathematically by Stephen Hawking in 1974 and announced in a paper that shocked the physics community, is that a black hole is not truly black. It glows, it radiates, it loses mass, so slowly as to be almost beyond description, but it does. And that glow is what will, across timescales that dwarf the current age of the universe by factors that language can barely contain, eventually consume the black hole entirely. We will spend the next part sitting with this radiation, understanding how it works, what it means, and why Hawking's discovery was one of the most important moments in the history of theoretical physics. But for now, let this be the turning point in the story. We have followed the black hole from its violent birth, through the strange geometry of its horizon, and into the bizarre interior where time itself points inward. And now, at the horizon, we have caught the first glimpse of the mechanism of its death. Not a violent mechanism, not a dramatic one, a whisper, a faint, almost imperceptible leak of energy into the universe, driven by the quantum nature of empty space. A slow, patient, inevitable unraveling that will play out across cosmic time. Let your breathing slow. Let the darkness of the black hole settle in your mind, that sealed sphere of geometry in an otherwise open universe. And hold the thought that even here, in the most absolute darkness physics can describe, something is happening at the boundary. Something is leaking through, not fast, not in any way that you could measure today or that any telescope in the observable universe could detect for a black hole of any mass we currently know. But it is happening. The flaw is there. The clock is running. The universe, patient and quiet, has already begun the process that will end everything. Sleep well with that. We are not at the end of the story. We are just past the beginning. And the rest, the quantum mechanics, the thermodynamics, the information paradox, the trillion-year timescales, the final burst, all of that is still ahead of us, waiting in the dark, patient as the black hole itself. We have arrived at one of the most important ideas in this entire story. We touched it at the end of the last part, the idea that empty space is not empty, that the quantum vacuum seethes with fluctuations, and that near a black hole's horizon, something remarkable happens to those fluctuations. Now let's sit with this more carefully, because the discovery of Hawking radiation is not just an interesting detail in the biography of a black hole. It is one of the deepest results in all of theoretical physics. It is the place where two of the greatest theories humans have ever constructed, general relativity and quantum mechanics, meet for the first time. And what they produce when they meet is both beautiful and unsettling. To tell this story properly, we need to first understand a little more about quantum fields, not the mathematics. We will keep this gentle and slow. But the concept, the picture, the way physicists think about the world at its most fundamental level. In modern physics, the basic stuff of the universe is not particles. It is fields. A field is a quantity that exists at every point in space, taking some value at each point, which can vary from place to place and from moment to moment. The electromagnetic field, for example, exists everywhere in space. When it is disturbed, those disturbances propagate as waves, and we call those waves light. And when those waves are quantized, when we apply the rules of quantum mechanics to them, we get what we call photons, the particles of light. But photons are not fundamental objects in themselves. They are excitations of the electromagnetic field. They are ripples. They are the quantized disturbances of a deeper underlying reality. Every type of particle in nature corresponds to a quantum field of this kind. Electrons are excitations of the electron field. Quarks are excitations of the quark field, and so on for every particle in the standard model of particle physics. The universe, at its most fundamental level, is a collection of overlapping fields stretching across all of spacetime. And the vacuum, what we call empty space, the space where no particles are present, is the lowest energy state of all these fields simultaneously. It is the state where the fields are as quiet as they can possibly be. But here is the key point. The quantum mechanical rules that govern these fields say something surprising about that lowest energy state. They say that the fields cannot be perfectly still. They cannot have a precisely zero value everywhere at once. This is a consequence of the Heisenberg uncertainty principle, one of the foundational results of quantum mechanics. The uncertainty principle says that certain pairs of quantities cannot both be known with perfect precision simultaneously. The more precisely you know one, the less precisely you can know the other. For fields, a version of this applies to the value of the field and the rate at which it is changing. A field that is perfectly still would have both quantities known precisely, and that is forbidden by the uncertainty principle. So the fields must fluctuate. They must jitter. They cannot be perfectly calm even in their lowest energy state. These fluctuations of the vacuum are the virtual particles we mentioned earlier. They are not particles in the sense of being observable objects moving through space. They are fluctuations of the field, brief departures from the ground state that pop into existence and disappear again before they can be observed directly. In flat, ordinary spacetime, they come in pairs, a particle and its antiparticle, created together and annihilating together. They borrow energy from the vacuum for a moment and give it back. They leave no lasting trace. Now bring in the black hole, or more precisely, bring in the event horizon, and think about what happens to these vacuum fluctuations in the highly curved spacetime near the horizon. When a particle-antiparticle pair fluctuates into existence very close to the event horizon, something can happen that does not happen in flat spacetime. One of the pair can find itself on the inside of the horizon, its future pointing inward, while the other finds itself on the outside, its future still pointing outward, still connected to the exterior universe. In flat spacetime, they would annihilate, but here, the horizon intervenes. The one on the inside cannot come back out to meet its partner. The one on the outside has no partner to annihilate with, and so it becomes real. It becomes a genuine particle with genuine energy that propagates outward into the universe. It becomes what we call Hawking radiation. But where does the energy come from? Energy must be conserved. That is one of the most fundamental laws of physics. If a real particle escapes to infinity carrying positive energy, something else must carry negative energy. And in the curved spacetime near the horizon, it is possible for the infalling partner to carry negative energy, a concept that is forbidden in flat spacetime but is permissible in the highly curved geometry near a horizon. The infalling partner, carrying negative energy, crosses the horizon and effectively reduces the mass of the black hole. The escaping partner, carrying positive energy, flies outward and becomes part of the thermal radiation that the black hole emits. The net result is that the black hole has lost mass and the universe has gained energy. The process is continuous. Every moment, vacuum fluctuations near the horizon are being split by the geometry. One partner escaping, one falling in with negative energy, the black hole slowly, almost incomprehensibly slowly, losing mass. The black hole is not actually converting its mass into radiation in a direct sense. Rather, the curved spacetime near the horizon is enabling the vacuum to do something it cannot do in flat spacetime, to permanently separate pairs that would ordinarily recombine. And the energy of that separation is paid for by the black hole's mass. This picture, the picture of virtual pairs being split by the horizon, is actually a simplified description that Hawking himself used to explain the result to non-specialists. The full mathematical derivation is more involved. Hawking worked in the formalism of quantum field theory in curved spacetime, calculating how quantum fields behave when the spacetime they live in is curved by a black hole. What he found, after a calculation he initially expected to give 0, was a non-zero temperature. The black hole radiates like a body with a specific temperature that depends on its mass. A smaller black hole is hotter. A larger one is cooler. A stellar mass black hole has a temperature that is less than a billionth of a degree above absolute zero, cooler than anything else in the observable universe. When Hawking first completed this calculation, he thought he had made an error. The result was too surprising. A black hole has a temperature. A temperature implies radiation. Radiation implies energy loss. Energy loss implies mass loss. And mass loss, carried to its logical conclusion, implies that the black hole will eventually evaporate completely. This was not what anyone expected. The prevailing understanding at the time was that black holes were permanent. Once formed, a black hole, by the classical rules of general relativity, could only grow. Nothing could come out. Mass could only go in. The horizon could only expand. A black hole, classically, was immortal. Hawking's result overturned that, not immediately and not dramatically. The evaporation is so slow for any astrophysically realistic black hole that it is utterly undetectable with any instrument that exists or could realistically be built. But in principle, the process is real. The temperature is real. The radiation is real. And the implication is inescapable. Given enough time, and the universe will provide enough time, even the most massive black hole will eventually lose all of its mass and cease to exist. The physics community was initially skeptical. Several leading physicists pushed back. Hawking's calculations seemed to require reconciling things that could not be reconciled. The smoothness of classical spacetime and the discreteness of quantum mechanics, the absolute impermeability of the horizon, and the propagation of radiation outward from it. But over the decades since 1974, the result has been confirmed through multiple independent approaches, using different mathematical frameworks and different physical arguments. Today, Hawking radiation is accepted by essentially the entire physics community as a real physical effect, even though it has never been directly observed. And it is the key to everything that follows in the story of the black hole's death. So hold that picture. The event horizon, that sealed boundary in spacetime, surrounded by a seething quantum vacuum. The vacuum fluctuating constantly, pairs of particles appearing and disappearing. And occasionally in the curved geometry near the horizon, a pair being split, one escaping, one falling in, the black hole losing a tiny, almost immeasurably small amount of mass with every such event. The horizon glowing faintly, not in light that any telescope could detect today, but in a principle that changes everything about how we understand the ultimate fate of these objects. The universe is patient. And the black hole, the most absolute, the most sealed, the most permanent structure that classical physics can imagine, is losing mass. Grain by grain, quantum by quantum, slower than anything we have words for. But it is losing it, and that is everything. We have established something remarkable. A black hole has a temperature, it radiates, it loses mass. These three facts, following from Hawking's calculation, opened a door into a region of physics that physicists are still exploring today. Because once you accept that a black hole has a temperature, truly has a temperature, not metaphorically but physically, a cascade of other ideas follows. The most immediate of these is that a black hole is a thermodynamic object. It obeys the laws of thermodynamics. It has not just a temperature but an entropy. And the implications of that entropy are among the deepest and most troubling puzzles in all of fundamental physics. Let's take this step by step, because it is worth doing slowly. The laws of thermodynamics are among the most powerful and universal laws in physics. They were originally developed in the 19th century to describe heat engines, to understand the relationship between heat and mechanical work, to explain why certain processes happen spontaneously and others do not. But over time, it became clear that the laws of thermodynamics are not just laws about heat. They are laws about information, about the fundamental behavior of complex systems, about the relationship between the microscopic world of atoms and molecules and the macroscopic world of temperatures and pressures. The first law of thermodynamics says that energy is conserved. You cannot create energy from nothing, and you cannot destroy it. You can convert it from one form to another, but the total is always constant. This is the law that the energy carried away by Hawking radiation must be paid for by the mass of the black hole, a direct consequence of the first law. The second law of thermodynamics says that entropy, a measure of disorder or randomness, or more precisely, the number of microscopic arrangements of a system that are consistent with its macroscopic properties. Entropy never decreases in an isolated system. It stays the same or it increases, never decreases. This is the law that gives time its direction. Why does a cup of coffee cool down and not spontaneously heat up? Because heating up would require entropy to decrease, and entropy does not decrease. The second law is the reason the universe has a past and a future, a reason it evolves in one direction and not the other. Now, when physicists first began thinking about black holes in the context of thermodynamics, they noticed something troubling. If you throw a cup of coffee into a black hole, the coffee disappears behind the horizon. The coffee had some entropy, its heat, its disorder, the particular arrangement of its molecules. But once it falls into the black hole, that entropy seems to vanish. The black hole in classical general relativity is described completely by just three quantities: its mass, its spin, and its electrical charge. That is it. Three numbers. It does not matter if you throw in a cup of coffee, or a library of books, or a perfectly ordered crystal. The black hole described by the same three numbers is the same black hole. All the information about what went in seems to be gone. And if entropy is gone, the second law of thermodynamics seems to be violated. A young physicist named Jacob Bekenstein noticed this problem in the early 1970s and proposed a radical solution. He proposed that a black hole itself must have entropy, and not just a little, but an entropy proportional to the area of its event horizon. The horizon area, measured in units called Planck areas, is the entropy of the black hole. When you throw the cup of coffee in, the event horizon grows slightly. Its area increases, and that increase in area represents an increase in the black hole's entropy, enough to compensate for the entropy of the coffee that disappeared behind the horizon. The second law is saved, but at the cost of an extremely strange conclusion that the entropy of a black hole, a measure of its disorder, its information content, its complexity, is not proportional to its volume, as you might expect for an ordinary object, but to the area of its surface. This is called the Bekenstein bound, and it leads directly to one of the most profound ideas in modern physics, the holographic principle. If the entropy of a black hole is proportional to its surface area, then in some sense, all the information about the interior of the black hole is encoded on the horizon. The interior is not holding information in the way that a room holds information. The surface, the horizon, is holding it. The three-dimensional interior is, in some deep sense, encoded in the two-dimensional surface. This is what the holographic principle says, and it is now believed by many physicists to be a general feature of the universe, not just of black holes. The holographic principle suggests that any region of space can be fully described by the information on its boundary. The three dimensions we experience may be, in some sense, a projection of information encoded on a two-dimensional surface. This is not science fiction. It follows from the mathematics of string theory, from work in the 1990s by Juan Maldacena showing a precise mathematical equivalence between a theory of gravity in 3 dimensions and a quantum field theory on the 2-dimensional boundary of that space. The holographic duality, as it is called, is one of the most celebrated results in theoretical physics of the last 30 years. But all of this comes back, ultimately, to Hawking radiation. Because once we accept that a black hole has entropy and that the entropy is encoded on the horizon, and that Hawking radiation slowly carries energy away from the black hole, the question becomes, what happens to the information? What happens to the information about the cup of coffee, the library of books, everything that ever fell into the black hole? Does it come out with the Hawking radiation, or is it destroyed? This is the information paradox, and it is one of the most important unsolved problems in theoretical physics. It is not a small technical puzzle. It cuts to the heart of whether quantum mechanics itself is consistent with general relativity, because quantum mechanics has a principle called unitarity, which says, in essence, that information is never destroyed. Physical processes may scramble information, may render it practically inaccessible, but they never truly erase it. The microscopic laws of quantum mechanics are reversible. If you know the final state of a system perfectly, you can always, in principle, work backward to find the initial state. Information is conserved. But if a black hole forms, absorbs information, and then evaporates in Hawking radiation that carries no information, pure thermal radiation, like the glow of a hot ember, then information has been destroyed. The initial state, the particular arrangement of matter that fell in, cannot be recovered from the final state, the Hawking radiation. That would violate unitarity. That would mean quantum mechanics is not, in fact, complete. Stephen Hawking believed for many years that information was genuinely lost. He thought the black hole evaporation process was truly irreversible, that the formation and evaporation of a black hole created new situations in nature that quantum mechanics could not accommodate. He thought it was necessary to modify the rules. Most of the string theory community disagreed. They believed, on the basis of the holographic duality, that information must be preserved, that somehow, in a way not yet fully understood, the Hawking radiation must carry the information out, scrambled beyond any practical hope of recovery, but present in principle. In 2004, Hawking conceded the debate. He accepted the argument that information is likely preserved, that the evaporation of a black hole, despite appearances, is a unitary process. But he could not, and still today no one can fully explain, the mechanism by which the information escapes. How does information that fell through an apparently impenetrable horizon manage to encode itself in the radiation that comes from the vicinity of that horizon? The mathematics says it must. The full picture of how it does so is still incomplete. This is where we leave the information paradox for now, not with a resolution but with a question. And questions, held gently in the mind before sleep, can be more productive than answers. The black hole knows something about everything that ever fell into it. The universe insists that knowledge is never destroyed. The horizon stands between them, and somewhere in the interplay between quantum mechanics and gravity, in the mathematics that we do not yet fully have, a resolution lies. Waiting, patient as the black hole itself, we have now laid the deep foundations. We understand the horizon, the interior, the quantum vacuum, Hawking radiation, temperature, entropy, and the information paradox. We are ready at last to follow the black hole forward through time, to watch it age, to watch the radiation slowly, almost imperceptibly, steal its mass away across timescales that will require us to think in entirely new units, and to follow it eventually, all the way to its end. But that journey through time begins in the next part. For now, rest here. The foundations are solid, the questions are deep, the universe is patient, and the black hole is waiting. We have spent time in the deep foundations. We have learned that a black hole has a temperature, that this temperature arises from the quantum behavior of fields near the event horizon, and that this temperature means the black hole radiates energy, loses mass, and will eventually evaporate. Now it is time to make this concrete, to put numbers to it. Not to overwhelm you with arithmetic, but to give the temperature and the timescale a shape that you can hold, even if only loosely, in your mind. Because without some sense of the numbers, the true strangeness of the story is lost. The evaporation of a black hole is not merely slow. It is slow in a way that requires entirely new categories of thought. Let us begin with the temperature. Hawking showed that the temperature of a black hole is inversely proportional to its mass. The more massive the black hole, the lower its temperature. The less massive it is, the hotter it glows. This inverse relationship is one of the strangest features of black hole thermodynamics, because it is the opposite of what we expect from ordinary objects. When you heat an ordinary object, it radiates more and eventually loses energy, cools down, and reaches equilibrium with its surroundings. When a black hole radiates, it loses mass, and losing mass makes it hotter, which makes it radiate more, which makes it lose mass faster. A black hole does not cool down as it evaporates, it heats up. The evaporation is not a gradual cooling to equilibrium. It is a runaway process, slow at first, then faster still, until the final moments when the temperature is immense and the last energy is released in a burst. But we are getting ahead of ourselves. Let us start at the beginning of that process, with a black hole that has just formed and is sitting, freshly made, in the universe, radiating at its initial temperature. For a black hole with the mass of the Sun, one solar mass, the Hawking temperature is approximately 60 nanokelvins. That is 60 billionths of a degree above absolute zero. To give you a sense of how cold that is, the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, has a temperature of about 2.7 Kelvin. That is nearly 50 million times hotter than the Hawking temperature of a solar mass black hole. The universe itself, in its current state, is far hotter than any astrophysical black hole. This means that any black hole with a mass comparable to a stellar mass black hole is currently absorbing radiation from its surroundings faster than it is emitting Hawking radiation. It is, in the present universe, gaining mass, not losing it. The net flow of energy is inward, not outward. This will change. As the universe expands and cools, the cosmic microwave background will thin and cool further. Eventually, in the very far future, the background temperature will drop below the Hawking temperature of even the most massive black holes. At that point, the black holes will begin to be net emitters. For the first time in their existence, they will be losing mass to Hawking radiation faster than they are gaining it from the environment. But that turning point is still unimaginably far in the future. For now, the black holes are bathed in a universe that is, from their perspective, warmer than they are. They absorb, they wait. For a supermassive black hole, one with 1 billion solar masses at its core, the Hawking temperature is even lower. It scales inversely with mass. 1 billion solar mass black hole is 1 billion times colder than a solar mass black hole. That means its temperature is something like 60 times 10 to the power of negative 18 Kelvin, a number so close to absolute zero that it has no comparison in any laboratory or natural setting we know. The universe cannot get this cold. No process in nature produces temperatures this low. The black hole is colder than anything, colder than the coldest point in intergalactic space, colder than the diluted afterglow of the Big Bang, colder than any state that nature otherwise achieves. And yet it is not at zero. It has a temperature. It radiates. Now let us think about the timescale. How long does it take for a black hole to lose all of its mass to Hawking radiation? The answer depends on the mass in a very specific way. The evaporation time is proportional to the cube of the mass. Double the mass, and the evaporation time increases by a factor of 8. Triple the mass, and the time increases by a factor of 27. The timescale grows rapidly with mass. For a black hole with the mass of the Sun, the evaporation time is approximately 2 times 10 to the power of 67 years. Let us write that out in words. 2 followed by 67 zeros. Years. The current age of the universe is approximately 14 billion years, which is roughly 10 to the power of 10 years. So a solar mass black hole will take 10 to the 67th years to evaporate, a number that is 10 to the 57th times longer than the current age of the universe. That is 10 million billion 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 times longer than the universe has existed so far. There are no good analogies for this. Every analogy breaks down. If you compared a second to the age of the universe, and then compared the age of the universe to 10 to the 67th years, you would still have a number far too large to make intuitive sense. The timescale of a solar mass black hole's evaporation is simply beyond any frame of reference that human experience provides. We are not talking about a long time in the way that the age of the universe is a long time. We are talking about something qualitatively different, a timescale so vast that everything we know about the universe, everything that currently exists within it, will long since have changed beyond recognition. For a supermassive black hole, it is worse still. A black hole with 1 billion solar masses has an evaporation time proportional to the cube of 1 billion times the solar mass evaporation time. 1 billion cubed is 10 to the 27th, so its evaporation time is approximately 10 to the 94th years. 10 to the 94. Written out, that is a 1 followed by 94 zeros. Years. To say this number is beyond comprehension is an understatement so vast as to be almost itself incomprehensible. And yet these numbers are not guesses. They follow from the mathematics of Hawking radiation with the same inevitability that the orbit of a planet follows from Newton's laws. They are what the physics says. The universe has the patience and the time for them to be real. What do we do with numbers this large? How do we hold them in mind without simply becoming numb? One approach is to think of them not as quantities to be grasped, but as landscapes to be inhabited. The way you do not need to know the exact number of grains of sand on a beach to feel the beach beneath your feet. You do not need to hold 10 to the 94 in your mind, all at once to let its immensity wash over you, to let it communicate something about the nature of the universe. The universe is not in a hurry. The universe has arithmetic that we evolved minds did not need to understand in order to survive on the African savanna. And so it confronts us with numbers that sit outside our intuition, outside our feeling, outside our ability to compress into a single image. They require a different relationship, not understanding, not visualization, something more like acceptance. The black hole is patient. It has all the time there is. And from its perspective, if we are allowed to speak of a black hole having a perspective, the slow leak of Hawking radiation is happening every moment, imperceptibly, grain by grain, quantum by quantum. The temperature is barely above zero. The radiation is cooler than anything. The mass loss is so slow that in the entire current age of the universe, a solar mass black hole has not lost a single proton's worth of mass to Hawking radiation. Not one proton, in 14 billion years. And yet the clock is running. The process is real. The end, however impossibly far away it is built into the physics from the moment the black hole forms. The death is written into the birth. The evaporation is encoded in the horizon. And time, the same patient, indifferent time that built galaxies and evolved life and watched civilizations rise and fall, will carry the process forward, one quantum fluctuation at a time until nothing is left. Let that settle into you. 10 to the 67, 10 to the 94, not as numbers to remember, but as a feeling of scale so vast that it redefines what we mean by patient. A feeling of permanence that is, paradoxically, impermanence drawn out to its logical extreme. The black hole will die. It will just take a very, very long time. And in that very, very long time, while it waits, the rest of the universe will undergo changes that dwarf anything we can currently imagine. Let us, in the next part, begin to explore what that universe looks like. The universe that the black hole will outlive, and what it means that these patient, dark objects will be among the last things standing when everything else has changed. For now, close your eyes a little more. Let the numbers drift. Let the temperature, 60 billionths of a degree, be a kind of background hum in your imagination, barely perceptible, almost zero, but not zero, never quite zero. The faintest possible glow in the deepest possible dark. That is the black hole, patient and almost imperceptibly warm, waiting out the ages. To truly follow the black hole across its immense lifespan, we need to understand the universe it will outlive. We need to picture the cosmos as it will be, not in 1,000 years or 1,000,000, but in timescales so large that the universe we currently inhabit will be unrecognizable. Because the death of a black hole does not happen in the universe we know. It happens in a future so distant that the stars will be gone, the galaxies will have dispersed, and the fundamental particles themselves may have undergone changes we can barely speculate about. To appreciate the patience of the black hole, we must first appreciate everything that it will outlast. Let us start closer to home and move outward in time. The universe today is about 14 billion years old. It is a vibrant, busy place by cosmic standards. Stars are being born in clouds of gas and dust. Galaxies are colliding and merging. The cosmic microwave background is cooling as the universe expands. Life, at least in one small corner of one unremarkable galaxy, has developed and is asking questions about black holes. This is our moment, relatively early in the story, though it does not feel that way from the inside. Move forward in time to about 100 trillion years from now. 10 to the 14 years. This is the era that cosmologists call the stelliferous era, the age of stars. All of the star formation that is currently happening and will happen in the future will be essentially complete by this point. The last stars will be burning out. The universe will have used up most of its available hydrogen, the fuel for stellar fusion. Small, dim, red dwarf stars will be the last to go. They burn their fuel so slowly and so efficiently that they can last for trillions of years. But even red dwarfs have a limit. Around 10 to the 14 years, the last red dwarf will exhaust its hydrogen, swell briefly, and fade into a cold, dark remnant. The stelliferous era will end. The universe will go dark in a way it has not been dark since before the first stars lit up. What is left after the last stars die? The remnants of stellar evolution, white dwarfs, neutron stars, and black holes. White dwarfs are the cooling embers of stars like our sun, dense spheres of carbon and oxygen, no longer fusing, slowly radiating away the heat they have accumulated over their lifetimes. They cool and dim over trillions of years. Neutron stars are the crushed remnants of more massive stellar deaths, dense balls of neutrons held up against gravity by quantum mechanical pressure. They too cool and fade, becoming dark, cold, ultra-dense objects drifting through the dark of the former galaxy. And black holes remain, of course, but the universe around them is increasingly dark. Move further forward in time to around 10 to the 30 years from now. This is the era known as the degenerate era, where the universe is populated mostly by these cold remnants, brown dwarfs, white dwarfs, neutron stars, and black holes. There is no new starlight. Galaxies no longer blaze. The universe is dark and cold by any measure, but interesting things are still happening at the quantum scale. White dwarfs and neutron stars, over these immense timescales, may slowly cool to near absolute zero. Brown dwarfs, objects that were never quite massive enough to ignite fusion, drift through the dark. Gravitational interactions occasionally cause remnants to collide or be ejected from the loose structures that once were galaxies. And then there is the question of proton decay. One of the predictions of many grand unified theories in particle physics, though not yet experimentally confirmed, is that protons are not absolutely stable. Over timescales of around 10 to the 33 to 10 to the 40 years, protons may spontaneously decay into lighter particles. A positron and a neutral pion, for example, which then quickly decay further into photons and other lighter particles. If proton decay occurs, then over these timescales, all ordinary matter, all atoms, all molecules, all the material that makes up white dwarfs and neutron stars and planets and anything else that is not a black hole, will eventually dissolve, not through any dramatic process. Slowly, one proton at a time, the material objects of the universe will quietly disintegrate, their constituent particles decaying into radiation. This is a significant juncture in cosmic history. If proton decay occurs, then around 10 to the 40 years, the universe will contain no ordinary matter at all. No atoms, no molecules, no chemistry, no material structure of any kind that is not sustained by something other than the stability of the proton. The universe will consist of photons, neutrinos, electrons, positrons, and black holes. Just radiation and gravity, drifting in an expanding, cooling space. And the black holes will still be there. They will have barely changed. A stellar mass black hole at 10 to the 40 years has lost such a negligible fraction of its mass to Hawking radiation that it is, for all practical purposes, identical to the black hole that formed 10 to the 40 years earlier. It has been patient in a way that nothing else in the universe has managed to be. While everything around it has transformed, stars burned out, galaxies dispersed, matter decayed, the black hole has simply waited, its geometry unchanged, its horizon intact, radiating so feebly that the change is unmeasurable. This is the nature of the black hole's patience. It does not merely outlast the stars. It outlasts the matter. It outlasts the chemistry. It outlasts everything that we normally think of as permanent. A mountain feels permanent to a human being, but a mountain is made of atoms, and atoms are made of protons. And if protons decay, the mountain eventually dissolves into a faint mist of radiation. Civilizations feel permanent to those within them, but civilizations are also made of protons, and they too will eventually dissolve. The black hole is different. It is not made of atoms. It is not made of protons. It is a feature of spacetime itself, a shape in the geometry of the universe. And spacetime, unlike matter, does not decay in any of the ways that matter decays. This is why the black hole's timescale is so much longer than everything else's. Everything else is ultimately made of particles, and particles can transform. The black hole is made of spacetime geometry, and geometry is more durable. Geometry changes through Hawking radiation, but Hawking radiation operates on timescales that make proton decay look hasty. A proton decays in 10 to the 33 to 40 years. A stellar mass black hole evaporates in 10 to the 67 years. A supermassive black hole evaporates in 10 to the 94 years. The black hole outlasts the proton by the same enormous margin that the proton outlasts a human heartbeat. So picture the universe at 10 to the 40 years. Dark, cold, expanding, empty of ordinary matter, only radiation and black holes. And in that emptiness, the black holes sit, their horizons glowing at temperatures so low they barely register against the cold of space, their mass barely changed from birth. They are not the last things in the universe because they are strong in any conventional sense. They are the last things because they are made of something the universe does not easily dissolve. They are the last things because space and time, the fabric they are woven from, is the most durable substance there is. And then eventually even that durability runs out. Because Hawking radiation, slow as it is real. And given enough time, given the kind of time we are discussing, even the most massive black hole will lose mass. Not quickly, not dramatically, but steadily. Grain by grain, quantum by quantum. The temperature will be rising imperceptibly at first. The radiation will be increasing, still far below any threshold of detection by any hypothetical instrument. But the change is happening. The black hole's mass is thinning. The horizon is slowly, almost imperceptibly, shrinking. It will shrink for a long time, for a very, very, very long time, but it will shrink. And that is the key. Once the universe has crossed into the era where matter is gone and only radiation and black holes remain, once everything else has dissolved and dispersed, the black holes become the center of the story. Not because they are dramatic, because they are patient, because they are the last remaining structure, because the universe has narrowed its cast of characters down to its most enduring members, and those members are quietly, steadily, losing their grip on existence. From here, the story accelerates in a relative sense, not in absolute time, which continues to expand in ways that dwarf everything we have discussed, but in the arc of the narrative, we are past the middle. The universe has changed enormously around the black hole. The black hole has barely changed at all, but the conditions are shifting. The long wait before net evaporation begins is over. The universe is now cold enough, dark enough, empty enough that the black hole's Hawking temperature, tiny as it is, now exceeds the background temperature of the universe. For the first time, the black hole is the warmest thing around. For the first time, the balance has shifted. Energy flows outward. The evaporation, which was always happening in principle, now dominates the physics. The slow death has entered its next phase. Let that image settle. A dark, empty universe, expanding and cooling. The galaxies long gone, the stars long cold, the matter long dissolved, and in the dark a handful of black holes, patient survivors of everything the universe has thrown at time, beginning very slowly to thin. Not gone yet, not close to gone, but gone in the direction, pointed toward zero, moving so slowly that the word moving seems wrong, but moving, that is enough, that is everything. We have watched the universe around the black hole transform beyond recognition, the stars extinguished, the matter dissolved, the galaxies dispersed, And yet the black hole remains, its horizon intact, its geometry unchanged, its patience essentially infinite. Now let us follow the evaporation itself more carefully, not just in terms of timescale, but in terms of what is actually happening to the black hole as it slowly loses mass. Because the process of evaporation is not uniform. It does not tick along at a constant rate. It accelerates. And that acceleration, though imperceptible for almost the entire lifespan of the black hole, will become dramatic in the very end. To understand the shape of the evaporation, think again about the relationship between mass and temperature. We said that temperature is inversely proportional to mass. Halve the mass and the temperature doubles. Quarter the mass and the temperature quadruples. This inverse relationship means that as the black hole loses mass, it gets hotter. As it gets hotter, it radiates more intensely. As it radiates more intensely, it loses mass faster. Each step feeds the next in a self-reinforcing cycle that starts imperceptibly slow and ends with extraordinary speed. In the early phases of evaporation, this acceleration is completely invisible. A solar mass black hole loses mass so slowly that reducing its mass by even a small fraction takes a time comparable to its total evaporation lifetime. For the first vast swathes of its existence, the black hole is essentially constant. Its mass, its temperature, its horizon radius, all are effectively unchanged. The Hawking radiation is so feebly energetic that even speaking of it as radiation feels misleading. The quanta being emitted have wavelengths longer than the observable universe. They are not photons in any practical sense, not particles carrying energy in a way any detector could register. They are the faintest possible whisper of thermodynamic activity, a signal so buried in the noise of everything else that the word signal itself seems too strong. But the mathematics does not care about our ability to detect the signal. The mathematics says the mass is decreasing, and so it is. And the universe, as we established, will eventually reach a state where every other process has ceased. In that state, the mathematics has all the time it needs. Every whisper counts. Every quantum emitted is a step closer to zero. The slow accumulation of steps, carried out across timescales that dwarf everything we have discussed, will eventually add up to everything. Now let us think about the different kinds of black holes and how they differ in their evaporation. Because not all black holes are the same mass, and the differences in mass translate into enormous differences in character and in timing. The smallest black holes are the most interesting from the perspective of evaporation, because they are the hottest and they will evaporate the soonest. Stellar mass black holes, those born in supernova explosions from massive stars, typically range from a few solar masses to a few tens of solar masses. The lightest ones, around 3 to 5 solar masses, are the smallest stellar black holes we currently know of. Their Hawking temperatures are still incomprehensibly low compared to anything in the current universe, but they are warmer than the supermassive monsters, and their evaporation times, while still staggeringly long, are shorter by many orders of magnitude. A black hole of 5 solar masses will evaporate in roughly 10 to the 68 years, about 10 times longer than a solar mass black hole. This might seem like a trivial distinction, but in the context of how the story ends, it matters. The lighter black holes will evaporate first. They will reach their final moments first. They will produce their final bursts of energy first. And in a universe that has become almost perfectly dark and quiet, those final bursts will be the only events of any consequence for vast stretches of time. The heaviest stellar black holes, those born from particularly massive stars with masses of 20 or 30 solar masses, will take correspondingly longer. But the difference between 10 solar masses and 30 solar masses, cubed, is a factor of 27. And so the heaviest stellar black holes will take about 27 times longer than the lightest ones, still in the range of 10 to the 67 to 10 to the 69 years. Vast by any measure, but all roughly in the same ballpark cosmically speaking. Then there are the intermediate mass black holes, objects in the range of hundreds to hundreds of thousands of solar masses, thought to exist at the centers of smaller galaxies and in dense star clusters. Their evaporation times scale accordingly, pushing into the 10 to the 70 to 10 to the 80-year range. Longer still. And then there are the supermassive black holes. These are the giants, the objects at the centers of large galaxies, including our own Milky Way with its 4 million solar mass Sagittarius A, including the massive elliptical galaxies in clusters with their billion and 10 billion solar mass central black holes, including the legendary objects like the black hole at the center of Messier 87, which was famously imaged in 2019 and which contains about 6.5 billion solar masses. These objects have evaporation times of 10 to the 83 years for a million solar mass object, 10 to the 94 years for a billion solar mass object, and reaching toward 10 to the 101 years for the most massive known black holes. 10 to the 101 years. Let us sit with that for a moment. There is a famous number in physics called a googol, 10 to the 100. Simply as a name for a large number. The most massive black holes known will take longer than a googol of years to evaporate. And in the context of the universe's current age of roughly 10 to the 10 years, even a googol of years is so far beyond the present that it sits in an entirely different category of time. But here is the thing about all these numbers, as different as they are from each other. They are all finite. Every single one of them is a finite number. A solar mass black hole in 10 to the 67 years. A billion solar mass monster in 10 to the 94 years. A googol plus years for the most massive objects, all finite, all reachable in principle given enough time. And the universe, as far as we know, has enough time. The universe is not going to stop. The expansion will continue. The cold, dark, empty future will go on. And eventually for every black hole, regardless of mass, the end will come. There is something philosophically significant in this. We often think of size as conferring permanence. The large things outlast the small things. Mountains outlast anthills. Galaxies outlast stars. And it is true that more massive black holes take longer to evaporate, but the relationship is not infinite. Doubling the mass multiplies the evaporation time by 8, tripling it multiplies by 27. Making the black hole a billion times more massive multiplies the evaporation time by 10 to the 27. Impressive, but not infinite. No amount of mass buys true immortality. The evaporation time grows, but it always remains finite. The death is always written into the birth. No matter how large the black hole, the equation for its evaporation time returns a number. A very large number, but a number. This is one of the most profound things about Hawking radiation. It democratizes mortality. In classical general relativity, black holes are immortal. They can only grow. They are permanent features of spacetime. In quantum gravity, every black hole has a lifespan. Some lifespans are incomprehensibly long, but they are lifespans. No black hole is exempt. The equation does not allow exceptions. The universe is going to outlast all of them. The universe, expanding and cooling, will still be here, dark and vast and quiet, long after the last black hole has evaporated. It will be a universe of essentially nothing, photons and other light particles drifting in an expanding space, growing colder and more dilute as the expansion continues, approaching asymptotically something as close to absolute nothing as physics allows. And even then, perhaps, in a universe of almost nothing, the quantum vacuum will continue to fluctuate. Space will not be empty. It will never be truly empty. The universe will go on, changed beyond recognition, but going on. The black holes will be gone, but the universe that they occupied for so long will remain, changed by their presence, carrying in its thermal history the record of every quantum they ever emitted. The information that was scrambled and hidden in the Hawking radiation will be there, encoded in the correlations between particles so spread out, and diluted that recovering it would require a computational effort that makes the evaporation timescale look brief. But it will be there. Because the universe does not forget. For now, let us hold the image of the different black holes, stellar, intermediate, supermassive, patient in their different degrees, each with its own schedule, each moving toward the same destination at its own pace. Like travelers on a road of different lengths, all walking toward the same horizon. Some closer, some farther, but all walking. Let that image drift gently as we move toward the next part of the story, where we will begin to focus on the final stages of evaporation itself, when the pace of change finally becomes something other than infinitesimal. Let us focus now on the final stages. After all the patience, after all the waiting, after the universe has transformed and everything else has dissolved and dispersed, the moment finally arrives when a black hole's mass has dropped to the point where the evaporation starts to become noticeable, where the temperature is rising not imperceptibly but measurably, where the horizon is shrinking not by negligible fractions but by real fractions of its original size. We are not there yet in the story, not by many orders of magnitude in time. But let us look ahead to understand the shape of the ending. Because the ending of a black hole's life is one of the most dramatic events imaginable in physics, extraordinary in its contrast with the immense patience that preceded it. The key to understanding the final stages is that inverse relationship between mass and temperature, and its self-reinforcing nature. For most of the black hole's existence, the mass is so large and the temperature so low that the radiation is almost non-existent. The evaporation is happening, but at a rate so slow that in any practical sense, nothing is changing. Then, as mass decreases, the temperature rises slightly, the radiation rate increases slightly, the mass decreases slightly faster, which raises the temperature slightly more, which increases the radiation slightly more. For a very long time, this feedback loop operates so gently that it is completely invisible. The changes are real, but they are compounding at such a slow rate that trillion upon trillion of years pass with no visible acceleration. But eventually, the mass crosses a threshold where the acceleration becomes non-negligible, not in any absolute sense that we would call dramatic. The black hole still has an enormous amount of mass by everyday standards. But relative to its mass at formation, relative to its mass a short time before, the rate of change is accelerating in a way that the mathematics makes unambiguous. The black hole is now in the final stages of its evaporation, and those final stages, though they may still take vast stretches of time by our reckoning, are concentrated in the tail end of the total lifespan in a very specific mathematical way. The mathematics of Hawking evaporation says that the mass decreases as a cube root function of the remaining time. If you have a black hole with 1 unit of mass left and it will take 10 units of time to evaporate, then at 5 units of time, it will have roughly 63% of its mass remaining. At 9 units of time, it will have about 47% remaining. At 9.9 units of time, about 22%. At 9.99, about 10%. The mass is not decreasing linearly. It is decreasing in a way that concentrates more and more of the energy release into the final moments. This means that while the first 99% of the black hole's lifespan is spent losing only a tiny fraction of its mass, the final 1% of the lifespan sees an enormous amount of mass released. And within that final 1%, the final 100th% sees even more released proportionally. The endpoint is a cascade, an ever-accelerating release of energy that concentrates more and more power into shorter and shorter windows of time. And as the mass decreases and the temperature rises, the character of the Hawking radiation changes too. At low temperatures, a black hole radiates mostly the lightest possible particles, photons and gravitons, massless particles that can be produced even with tiny amounts of energy. As the temperature rises above the rest mass energy of various particles, those particles become available for production. Above about 10 to the 9 Kelvin, which corresponds to a black hole with a mass of roughly 1 billion kilograms, the temperature is high enough to produce electron-positron pairs. Above 10 to the 13 Kelvin, pion-antipion pairs. Above higher temperatures still, all the heavier particles of the Standard Model become available. At the very end, as the black hole approaches the Planck scale, all the degrees of freedom of all the known particles are being produced. The radiation is no longer a faint glow of photons. It is an explosion of every particle that physics knows about. The Planck scale is the natural unit of length and mass in quantum gravity. The Planck mass is about 22 micrograms, about the mass of a small grain of sand. When a black hole's mass drops to the Planck mass, it is entering completely unknown territory. At this scale, quantum gravitational effects are dominant. The curvature of spacetime is changing on scales comparable to the quantum fluctuations of spacetime itself. Our current theories, both general relativity and quantum field theory, break down. We do not know what happens at this scale. It is possible that the black hole explodes in a final burst of energy and disappears completely. It is possible that some small, stable remnant remains, a Planck mass relic that persists indefinitely. It is possible that something else entirely happens that we do not yet have the mathematical framework to describe. But the energy released in the final moments is significant. A solar mass black hole has converted its entire mass into energy by the time it finishes evaporating. And by Einstein's famous relation connecting mass and energy, the total energy released is enormous, equivalent to the energy of roughly 10 to the 47 joules for a solar mass object. For comparison, the entire energy output of the Sun over its 10 billion year lifetime is about 10 to the 44 joules. The final evaporation of a solar mass black hole releases about 1,000 times more energy than the Sun produces over its entire lifetime. But remember, almost all of that energy was released in the final fraction of a second. The last burst, the final flash, that final flash, the endpoint of 10 to the 67 years of patient, almost imperceptible leaking, is a gamma-ray burst of extraordinary intensity. For a brief, brilliant moment, a black hole that has been colder than the universe for almost its entire life becomes the hottest, most energetic thing in its vicinity. It does not go quietly. It does not fade gracefully into the dark. It ends in a burst, a brief, fierce, final release of everything that was left. all the accumulated potential of mass energy converting itself into radiation in the last moments of existence. And then it is gone. The event horizon shrinks to zero. The geometry that defined the black hole dissolves. The singularity, whatever it truly was, ceases to exist as a singularity because the mass that curved spacetime into that configuration is gone. Where there was once a sealed region of spacetime, there is now just spacetime, flat, empty, expanding. The event horizon was not destroyed, it was not breached. It simply shrank to nothing as the mass that created it was radiated away. The sealing of the future that we described at the beginning, the geometry that pointed all futures inward, gradually relaxed as the mass decreased, and finally, when the last bit of mass was gone, it relaxed completely. Open space-time. The lock is gone because the door is gone. This is the end of the black hole. After all that time, after all that patience, after outlasting every star and every atom, a flash, a brief, violent, final emission of energy, and then nothing. Space-time, flat and empty and expanding, carrying the Hawking radiation outward in all directions. The information encoded in the correlations of that radiation, spreading into the universe, scrambled beyond any practical recovery but there in principle. The universe remembers, but we have moved ahead of ourselves. We have glimpsed the end. Now we need to return to the middle of the story and walk more carefully through the stages. Because between where the universe is now and those final moments, there are phases of the black hole's life that are worth exploring in their own right, not just as waypoints on the road to death, but as stages of existence that have their own character, their own physics, their own place in the story. Let us step back and think about the middle period, the long, dark, patient middle of the black hole's life, and what it means for the universe that surrounds it. For now, though, let the image of that final burst sit with you. After 10 to the 67 years or 10 to the 94 years of almost perfect darkness, a flash, brief and brilliant, and then nothing. Not nothing in the sense of emptiness as a threat or a loss. Nothing in the sense of completion. The story told from beginning to end. The geometry of spacetime returning to its natural, unforced state. The energy, all of it, returned to the universe from which it was originally drawn. There is something deeply satisfying about that, about endings that are complete, about processes that run all the way to their conclusion. The universe is a place where things that begin also end, and the ending of a black hole is, in some sense, the most thorough ending in physics. Every bit of mass converted. Every bit of information preserved somewhere in the radiation. The horizon dissolved. The geometry released, all the way to zero. That kind of completeness, that thoroughness, that following through is worth sitting with before sleep. We are almost through the arc of the story. In the parts that follow, we will come back to the information paradox and what the final evaporation implies for it. We will sit with the philosophical weight of these ideas, and we will find our way back to the quiet room you are resting in now, with a sense of the universe that is perhaps a little larger and a little more patient than it seemed before. But first, rest. The black hole is patient. You can be too. We have glimpsed the final burst. We have seen, in outline, the arc of the story from formation to dissolution. Now let us step back into the middle of that arc and think about something we have touched but not fully explored. What the long, patient evaporation of a black hole implies for the deepest question the whole story raises. The question of information. The question of what happens to everything that ever fell in. Because the final evaporation is not just the end of the black hole's existence. It is the resolution, or the non-resolution, of the most serious problem in theoretical physics of the last 50 years. Let us return to where we left the information paradox. We established that quantum mechanics has a principle called unitarity. That information is never destroyed. That in principle, the initial state of any physical system can always be recovered from its final state, at least in principle, given perfect knowledge of the final state. We established that if a black hole absorbs matter and then evaporates in perfectly thermal, featureless Hawking radiation, that information appears to be lost, and that would violate unitarity, one of the deepest principles of quantum mechanics. We noted that Stephen Hawking initially believed information was genuinely lost, and that most of the string theory community believed it was preserved, and that in 2004, Hawking conceded the debate. But conceding that information is probably preserved is not the same as explaining how, and the how is everything, because the how requires understanding what is actually happening at the horizon during the evaporation, and that requires a complete theory of quantum gravity that we do not yet have. Let us walk through the problem more carefully. A black hole forms from a collapsing star. The star was made of specific atoms in specific arrangements. Those atoms had a precise quantum state, a specific configuration of all their particles with specific properties. All of that information fell through the horizon as the star collapsed. Inside the horizon, it is presumably doing something. The infalling matter is presumably still there in some form, evolving. But we cannot see inside the horizon. We cannot access it. From outside, the black hole looks like a featureless object characterized by only three numbers: mass, spin, and charge. Now the black hole begins to evaporate. Hawking radiation is emitted from the horizon region. Early in the evaporation, this radiation is thermal. It looks like the radiation from a glowing body with a specific temperature, with no information content beyond that temperature. If you look at the radiation coming off, you cannot tell whether the black hole was formed from a star of hydrogen or a star of iron, from a collapsed cloud of gas or a pile of textbooks. All you see is thermal radiation, featureless, indistinguishable regardless of what went in. If the radiation remains featureless all the way to the end, and if the black hole finally disappears, then the information about the initial state is gone. The final state, a cloud of thermal radiation, does not carry a record of the initial state. The transformation is irreversible. Unitarity is violated. But if unitarity is preserved, if information is not lost, then the radiation cannot be truly thermal. It must carry, encoded in extremely subtle correlations between emitted particles, a complete record of everything that ever fell in. The radiation from a black hole that formed from hydrogen must be subtly different from the radiation from a black hole that formed from iron, different in correlations so delicate that they would require measuring essentially every particle in the entire history of the black hole's evaporation with perfect precision to detect. But the differences must be there. The question is how? How does information that fell through what appears to be a one-way door make its way back out in the radiation? One class of proposals goes by the name black hole complementarity. This idea, developed largely by Leonard Susskind, says that there is no contradiction, but only because no single observer can see both the interior and the exterior simultaneously. From the perspective of an observer far from the black hole, the infalling matter never actually crosses the horizon. Due to the extreme time dilation near the horizon, the infalling matter appears to slow down, to hover just outside the horizon, to be gradually scrambled and re-emitted as Hawking radiation. From this outside perspective, the information never went in. It was always outside, being processed and re-emitted. From the perspective of an infalling observer, on the other hand, the horizon is crossed without incident. The matter falls in. The singularity is in the future. The interior exists. From this inside perspective, the information definitely went in. Both perspectives are correct. Both are self-consistent. And crucially, they are not simultaneously accessible to any single observer. The outside observer can never go in and compare notes with the infalling observer without themselves crossing the horizon and losing access to the outside. There is no experiment that can catch the universe in a contradiction, because the two descriptions apply to observers who can never share information. This is complementarity. The information is both inside and outside, depending on your perspective, and no single perspective sees both. But complementarity has a problem. In 2012, 4 physicists, Ahmed Almeri, Donald Maroff, Joseph Polchinski, and James Sully, known by the acronym AMPS, pointed out a serious inconsistency. They argued that if you take seriously both the unitarity of the evaporation and the equivalence principle of general relativity, which says that the horizon should be smooth, and an infalling observer should feel nothing unusual when crossing it, you get a contradiction. Specifically, they showed that for information to come out in the Hawking radiation in a way that preserves unitarity, the early Hawking radiation and the late Hawking radiation must be entangled in a specific way. But this entanglement is incompatible with the smooth horizon that the equivalence principle requires. The two cannot both be true. Something must give. Their proposed resolution was dramatic. They suggested that the horizon is not smooth, that an infalling observer does not cross it without incident, that instead there is a firewall at the horizon, a sheet of extremely high energy radiation, and anything that falls in is immediately incinerated. The interior of the black hole in this picture does not exist in the usual sense. The information never went in because nothing survived crossing the horizon. This is an extreme conclusion, and it is deeply unsatisfying to many physicists. It violates the equivalence principle in a dramatic way. It suggests that the black hole has no interior, which contradicts everything that general relativity tells us about what happens when a massive object collapses. The debate spawned by the AMPS paper continues today. Various resolutions have been proposed, involving ideas about entanglement structure, quantum error correction, the nature of spacetime emergence, and connections between quantum information theory and quantum gravity. None has achieved consensus. One of the most intriguing recent ideas comes from the work on something called the Page curve. Don Page showed in the 1990s that if information is preserved, the entropy of the Hawking radiation must follow a specific curve over the lifetime of the black hole. It starts low, rises to a maximum at around the halfway point of the evaporation, and then decreases back to zero at the end. This curve, called the Page curve, is the signature of unitary evaporation. Recent work using ideas from quantum gravity and holography has shown that the entanglement entropy of the Hawking radiation does indeed appear to follow the Page curve, providing strong evidence that information is preserved, but without yet providing a complete physical picture of how. The information paradox is not resolved, but the direction of travel is clear. Information is preserved. The Hawking radiation, featureless as it looks, carries the record. The how is the remaining question, and answering it completely will require the full theory of quantum gravity that physicists are still working toward. It is one of the great open questions, not in the sense of being unanswerable, but in the sense of being unanswered yet. A question whose resolution will likely reshape our understanding of space-time, information, and the nature of reality at its most fundamental level. For our purposes tonight, the important thing is this. The evaporation of a black hole is not a loss. It is a return. Everything that fell in, all the matter, all the information, all the quantum states, is returned to the universe in the form of Hawking radiation, scrambled beyond any practical recovery, encoded in correlations so subtle that extracting the information would be effectively impossible. But there, the universe keeps its accounts. Nothing is truly destroyed. The black hole dies, but it does not take anything with it. It gives back everything, grain by grain, quantum by quantum, over timescales that dwarf the age of the universe. And at the very end, in that final burst, the last of it, the last information, the last mass, the last geometry, is released. That is a beautiful story. Not comfortable, not simple, not fully understood, but beautiful. An object of infinite patience giving back, slowly and completely, everything it ever took in. The most permanent structure in the universe turning out to be not permanent at all, but transformative. Not a destroyer, but a very slow, very patient, very thorough transmitter. Let that sit. The black hole is not the end. It is a pause, a very long pause, but a pause. And everything that paused inside it will eventually continue its journey through the universe, in a new form, scrambled and spread, but continuing. The universe does not forget. And neither, in the deepest physical sense, does it lose. We have walked through the physics of the information paradox, and we have arrived at a picture that is more hopeful than it might initially seem. Information is preserved. The Hawking radiation carries everything. The universe keeps its accounts. Now let us return to the physical journey of the black hole itself and follow it into the final stages of its existence. The long approach towards zero, the narrowing of the horizon, the acceleration of the process as mass decreases and temperature climbs. We are going to follow the last stages of a black hole's life in the way you might follow the last stages of a candle burning down, watching the flame change, watching the wax thin, watching the light shift character as the end approaches. But first, a word about what it means to say final stages, because the phrase is misleading without context. The final stages of a black hole's evaporation, the period during which the evaporation begins to accelerate noticeably, during which the temperature becomes significantly higher than it was at birth, occupy a vanishingly small fraction of the total lifespan in absolute time. And yet in absolute time, they still span spans that are enormous. Let us think about this with a specific example. Consider a stellar mass black hole of 10 solar masses. Its total evaporation time is on the order of 10 to the 68 years. If we define the final stages as the last 1% of that total time, the period during which the black hole has lost 99% of its original mass, that 1% still represents roughly 10 to the 66 years. 10 followed by 66 zeros. Years. The final 1% of a black hole's life is still longer, by an incomprehensible margin, than the current age of the universe. The final 1/100% is still longer than the current age of the universe. The final 1/1,000,000% is still longer than the current age of the universe. The compounding nature of the numbers means that even the very tail end of the evaporation occupies timescales that dwarf everything familiar. And yet, mathematically, the final stages are the most interesting, because the physics changes qualitatively as the mass decreases. The black hole's character, its relationship to the particles it emits, its temperature profile, and ultimately the nature of the radiation itself, all shift as the mass drops through successive thresholds. Let us trace those thresholds. When a black hole has the mass of a small mountain, roughly 10 to the 11 kilograms. Its Hawking temperature reaches about 1 billion Kelvin. At this temperature, the radiation begins to include electron-positron pairs. The black hole is no longer emitting only photons and gravitons. It has crossed the threshold at which its temperature corresponds to the rest mass energy of the electron, and so electrons and positrons are being produced from the intense thermal energy near the horizon. The radiation has become richer, more varied in its content, more energetic in its individual quanta. As mass drops further, through 10 to the 9 kilograms, 10 to the 8, 10 to the 7, the temperature climbs through billions and then trillions of Kelvin, and successively heavier particles join the spectrum of emitted radiation. Muons, pions, kaons, the heavier particles of the standard model become accessible. Each new threshold is crossed as the temperature rises past the energy equivalent of each particle's rest mass. The radiation spectrum is like a menu that grows longer and longer as the temperature increases, starting with only the lightest, most energetic items, photons and gravitons, and gradually adding heavier and heavier courses as the heat climbs. This progression continues until the black hole's mass drops to around 10 micrograms, the Planck mass. At this point, the temperature has reached approximately 10 to the 32 Kelvin, the Planck temperature, the highest temperature that has any meaning in current physics. At this temperature, all known particles are being produced. The black hole is radiating with maximum diversity, a complete spectrum of everything that physics knows. And at this point, the evaporation enters territory that our current theories cannot describe. The geometry of spacetime at the scale of the Planck mass is governed by quantum gravity, and quantum gravity, as we noted, is a theory we do not yet fully have. The Planck mass is remarkably small by the standards of black holes, 22 micrograms, smaller than a grain of sand. A black hole that started with 10 solar masses, roughly 10 to the 31 kilograms, has shed all but 10 to the -8 kilograms of its original mass before it enters this unknown regime. It has given back through Hawking radiation essentially everything it ever had. It has reduced itself from a compact remnant of a massive star to something smaller than a grain of sand, and it has done this over timescales of 10 to the 68 years. The final grain of sand-sized stage, the Planck mass, is reached after all that time, all that patience, all that slow and imperceptible leaking. What happens next? This is the question that quantum gravity must answer, and it cannot yet. Several possibilities present themselves. The first and most commonly assumed in the absence of a full theory is that the black hole simply evaporates completely. The last Planck mass of energy is emitted in a final burst. The horizon shrinks to zero. The geometry returns to flat spacetime, and the black hole ceases to exist. This is the complete evaporation scenario. It is clean. It is satisfying. It requires that the information be returned entirely in the Hawking radiation, which we have reason to believe is the case. The second possibility is that the evaporation slows and stops at the Planck scale, that some stable remnant of Planck mass is left behind. This remnant would be a Planck scale object with a mass of 22 micrograms and a physical size of roughly the Planck length, about 10 to the -35 meters, smaller than any scale we have ever probed or could probe. This remnant would be effectively invisible and essentially interaction-free at low energies. It would persist indefinitely, a tiny, stable relic of what was once a massive black hole. The appeal of this scenario is that it potentially resolves the information paradox by allowing the information to be stored in the remnant. But the cost is an infinite number of possible distinct remnants, since each one could contain the information from a different initial state, which creates its own theoretical difficulties. A third possibility involves something stranger still, that the Planck scale remnant is not stable, but transitions into something entirely different, a state of matter or spacetime that our current theories do not describe. Perhaps a kind of topological feature of spacetime, a baby universe connected to ours by a tiny throat that disconnects and goes its own way. Perhaps a fundamental string vibrating at the Planck scale. The honest answer is that we do not know, and the honest answer is also that not knowing is appropriate. This is the frontier. This is where physics reaches its current limit and stares into the dark. But here is what we do know and what is remarkable to hold. Whatever the final state, whether complete evaporation or Planck remnant or something else, we know what preceded it. We know the entire 10 to the 67-year journey. We know the slow beginning, the patient middle, the accelerating end. We know the thermodynamics and the information theory and the quantum mechanics of the horizon. We know the shape of the process with enormous confidence, all the way to the final grain of Planck scale mass. And that journey, that immense, patient, thoroughgoing journey, is the real story. The final moment is a punctuation mark at the end of a sentence that took longer to write than anything in the universe. There is something almost meditative about following this process all the way down. The black hole, so absolute and permanent and vast at its birth, 10 solar masses, an event horizon spanning 30 kilometers, has given back piece by piece its entire substance to the universe. It has not been destroyed by any external force. It has not been breached by any mechanism. It has simply, over unimaginable time, radiated itself away. The geometry that created it was sustained by mass, and as the mass departed, the geometry relaxed. The horizon shrank as the radius decreased. The temperature rose as the mass fell, and at the end there is nothing left to hold the shape. The curvature of spacetime, which bent so severely inward at the moment of formation, straightens out. Flat spacetime, open futures, nothing sealed. It is an ending that has the character of release, not an explosion that scatters debris, not a collapse into something else. A release. The geometry let go. The spacetime returned to its natural state. The mass, all of it, gone back to the universe from which it came, in a different form as radiation, as correlations in quantum fields spreading outward at the speed of light, but gone back. Nothing lost, nothing created, just transformed over the most patient transformation in the history of the universe. That is what the final stages lead to. That is what the long descent towards zero is heading toward. A release. And we will sit with what that means in the philosophical parts that are coming. But for now, let the physical picture settle. The black hole in its final stages. The mass thinning, the temperature rising, the particles diversifying, the horizon shrinking, the geometry relaxing, and at the end, one way or another, quiet, flat spacetime, open futures, the seal lifted. Rest in that image. After all the violence of formation, after all the patience of the long middle, after the gradual acceleration of the end, quiet. That is where it goes. That is where everything goes eventually. Quiet. We have traced the physical arc all the way to the threshold of the final moment, the Planck mass, the Planck temperature, the point where our theories reach their edge. Now let us do something that requires a different kind of attention. Let us slow down and imagine the last second. Not the last billion years, not the last million years, not even the last year, but the last second of a black hole's existence. What is happening in that final moment of a process that took 10 to the 67 years to arrive there? Because the last second is extraordinary. It is the most concentrated, most energetic, most dramatic event in the entire biography of the black hole. And it stands in such profound contrast to everything that came before it that sitting with it carefully can change how the whole story feels. To appreciate the last second, we need to appreciate what the second before it looked like, and the minute before that, and the year before that, and the 1,000 years before that. Let us work backward from the end. In the final 1,000 years before a stellar mass black hole evaporates completely, the black hole has a mass of roughly 10 to the 10 kilograms, about 10 billion kilograms. This sounds large by human standards. It is about the mass of a large mountain, but compared to the original mass of 10 solar masses, it is almost nothing, about 1/10 to the 21st of the original mass. The black hole has lost all but about a billionth of a billionth of a billionth of its original mass. And yet it still has 1,000 years to go. Its temperature at this point is around 10 to the 14 Kelvin, incredibly hot, hotter than anything in the current universe, hotter than the cores of the most massive stars, and yet still not at the Planck temperature, still not at the end. In the final year, the mass is smaller still, around 10 to the 8 kilograms, 100 million kilograms, the mass of a moderate-sized building. The temperature is around 10 to the 17 Kelvin. The radiation is intense. Every kind of particle known to physics is being produced in abundance. The black hole is a tiny, extraordinarily hot seething point of quantum production. It is nothing like the dark, cold, almost invisible object it was for the vast majority of its life. It has transformed into its opposite, from the coldest to the hottest, from the darkest to the most energetic, from the most patient to the most urgent. In the final second, the mass drops from roughly 10 to the 5 kilograms to 0, 100,000 kilograms, converted entirely to radiation in 1 second. By Einstein's famous relation, that corresponds to an energy release of roughly 10 to the 21 joules. For comparison, the largest nuclear weapon ever detonated released about 10 to the 17 joules. The final second of a black hole's evaporation releases about 10,000 times more energy than the most powerful nuclear explosion in human history, all in 1 second, all from a region of space smaller than an atomic nucleus, all in the form of the highest energy particles and radiation that physics can produce. That is the last second. A burst of energy so intense, so concentrated, so brief, that it represents a kind of cosmic exclamation point at the end of an almost incomprehensibly long sentence. The universe has waited 10 to the 67 years for this moment. The black hole has been patient beyond all description. And then, 1 second, and it is over. What does this final burst look like if there were any observer present to see it? Assuming the observer is at a safe distance, they would see a flash, a brief, brilliant explosion of gamma rays and other high-energy particles emanating from what was, an instant before, an almost invisible point source. The gamma rays would spread outward at the speed of light in all directions. The observer would measure an energy spectrum that peaks at extraordinarily high energies, corresponding to the Planck temperature, a spectrum unlike anything produced by any other process in the universe. In the dark, cold, empty universe of 10 to the 67 years in the future, a universe where nothing has happened for incomprehensible stretches of time, this brief flash would be the brightest, most energetic event in the observable universe. There would be nothing to compete with it. The stars are long gone. The galaxies are long gone. The ordinary matter is long gone. There is nothing else radiating, just the quiet expansion of dark, cold space, and then for 1 second this, and then nothing. The flash propagates outward and dilutes. The space where the black hole was is now just space, flat, empty, expanding. No geometry to mark where the horizon was. No remnant in the most likely scenario of anything that was there before. The information, encoded in the correlations of all the Hawking radiation that was emitted over the entire lifetime, is spreading outward at the speed of light in an increasingly diluted, increasingly hard to read form. But it is there. The universe has received it all. There is something almost poetic about the contrast between the vast patience and the brief ending. Think about what the black hole's biography looks like if you compressed it into a single day. In this compression, 10 to the 67 years corresponds to 24 hours. The formation of the black hole happens in the very first microsecond of that day, an instant of tremendous violence. For the remaining 23 hours, 59 minutes, 59 seconds, and nearly all of that final second, the black hole sits there, essentially unchanging, cold, dark, patient, radiating so feebly that nothing appears to be happening. And then, in the very last sliver of the last second of that compressed day, a flash, and it is done. The vastness of the patience and the brevity of the ending are not accidental. They follow directly from the mathematics, from the inverse relationship between mass and temperature, from the cubic relationship between mass and evaporation time. The universe has built a structure in which power is exercised slowly and released quickly, in which patience is almost infinite but endings are sudden, in which the approach to zero is asymptotic for almost all of the journey, and then abrupt at the very end. This is not unlike other processes in nature if you look for the pattern. A dam holds back water for years and then fails in minutes. A volcano accumulates pressure for centuries and then erupts in hours. A supernova progenitor star burns steadily for millions of years and then collapses in less than a second. The pattern of long patience followed by sudden release seems to be woven into the fabric of how energy and structure behave. The black hole is simply the most extreme example, the most patient, the longest waiting, the most concentrated at the end. And perhaps that pattern is telling us something. Perhaps the universe favors structures that accumulate slowly and release suddenly, that build potential over vast timescales, and then discharge it in brief, concentrated bursts. Perhaps there is something fundamental about the way energy seeks its lowest state, preferring to remain bound, to remain structured, to remain concentrated, and then giving way all at once when the threshold is finally crossed. Black holes are the apotheosis of this tendency. They hold their structure for longer than anything. They release it more suddenly than almost anything. They are the universe's most extreme demonstration of patience preceding release. For us, lying in the dark and thinking about this, there is something settling in that pattern. The idea that things hold their shape until they cannot and then let go. That the release, when it comes, is complete. That nothing is held back. That the ending is thorough. There is a kind of integrity in that, a completeness, a following through. The black hole does not evaporate halfway and then stop. It goes all the way. It gives everything back. 10 to the 67 years of patience, and then 1 second of release, and then nothing withheld. That is a form of completion that is rare and worth recognizing. Most things in the universe leave residues, leave traces, leave incomplete transformations. The black hole, in its final second, achieves something close to total transformation. And the universe, which has waited for that transformation with the same patience as the black hole itself, receives it completely. Nothing is lost. Everything is changed. Let that settle into your breathing. The last second of the black hole, bright against the dark, brief against the vast, complete against all the incompleteness that surrounds it, and then quiet again, just space. Open, expanding, empty space, carrying the memory of what was there, in the form of radiation spreading outward at the speed of light, thinning and cooling as the universe continues its own endless expansion. The black hole is gone. The universe continues. And somewhere in the correlations of that spreading radiation, everything that ever fell in is still, in principle, there. We have watched the last second. We have seen the flash. We have sat with the emptiness that follows it. Now let us ask a question that the final burst raises immediately, and that any honest account of this story must sit with. What remains? After the flash, after the Hawking radiation has spread outward, after the geometry has relaxed and the event horizon has shrunk to zero, is there anything left at all? Is the black hole truly gone, or does something persist? This question matters for more than philosophical tidiness. It matters for physics. If something remains, even something very small, then the story of the black hole has an additional chapter. If nothing remains, if the evaporation is complete, then the story ends at the flash and the question becomes purely about what the radiation carries and how it carries it. The answer turns out to be genuinely unknown, one of those places where the physics of the frontier meets the edge of what can currently be said with confidence. Let us start with the scenario most physicists find most natural: complete evaporation. In this picture, the black hole evaporates entirely. The mass reaches zero. The event horizon shrinks to zero radius. The spacetime geometry, which was so severely curved around the black hole, relaxes completely to flat spacetime. The region that was once inside the horizon is now accessible again in principle, though there is nothing inside it, since everything that fell in has been returned to the universe via Hawking radiation. The black hole is gone, not dormant, not transformed into something else, simply gone, in the way that a flame is gone when the last fuel is consumed. The process that sustained the geometry has run to completion. This scenario has a clean simplicity. It says that black holes are not permanent features of the universe but temporary ones. They are structures that form, persist for immense times, and then dissolve. They are part of the universe's thermodynamic story, a place where entropy is stored and slowly returned, a kind of escrow account for information and energy, holding the deposit for timescales beyond imagining, and then paying it all back with interest in the form of Hawking radiation. Complete evaporation is consistent with unitarity. If the black hole disappears entirely, then the information it once contained must be in the Hawking radiation. There is nowhere else for it to be. This is perhaps the strongest argument for complete evaporation. Not that we know it must happen, but that it is the scenario most consistent with the principle that information is not destroyed. If the black hole leaves behind a remnant, even a Planck scale one, then the information question becomes more complicated, because the remnant could potentially contain information, and the question of whether and how that information would ever be accessible becomes thorny. The Planck remnant scenario is the most commonly discussed alternative. In this picture, the evaporation slows and stops when the mass reaches the Planck mass, roughly 22 micrograms. At this scale, quantum gravitational effects become dominant, and these effects might stabilize the remnant against further evaporation. The remnant would be a Planck scale object, with a mass of 22 micrograms and a physical size of roughly the Planck length, 10 to the negative 35 meters. It would be stable. It would interact extremely weakly with ordinary matter. It would be effectively invisible. And it would carry encoded somewhere in its quantum state, the information about everything that ever fell into the black hole it descended from. The appeal of this scenario is that it avoids the need to explain how information escapes through the Hawking radiation in detail. The information just stays in the remnant. The problem is that this creates what physicists call the information remnant problem. Since each black hole can be formed from a different initial state, a different configuration of infalling matter, and since information is stored in the remnant, there must be an essentially unlimited number of different types of remnants, each encoding a different initial history, and objects with the same mass and charge and spin, but different internal information content would be distinct quantum states. An essentially unlimited number of distinct quantum states at the Planck mass would create problems for the thermodynamics of the system, in particular, for the calculation of how these remnants would contribute to things like the entropy of a gas of particles. An infinite number of distinct internal states would cause certain physical quantities to diverge to infinity, and infinity as an answer to a physical quantity is, as we noted before, almost always a sign that something is wrong. This objection is serious but not necessarily fatal. Various refinements of the remnant scenario have been proposed. Perhaps the information is not stored in local internal states, but in some kind of non-local encoding that avoids the divergence problem. Perhaps the remnant eventually does decay, but on a timescale so long that it appears stable by any practical measure. Perhaps the remnant picture is simply a description in one language of a process that looks like complete evaporation in another language, and the two descriptions are complementary views of the same underlying reality in the spirit of black hole complementarity. A third scenario, the baby universe, was proposed by some physicists as a way to reconcile the apparent loss of information with the requirements of unitarity. In this picture, the interior of the black hole does not evaporate. Instead, as the outer black hole evaporates, the interior pinches off from the exterior universe and becomes a separate, causally disconnected baby universe. The information that fell into the black hole goes with the interior, into the baby universe, and is not lost in the sense of being destroyed, but is lost in the practical sense of being in a universe that is no longer connected to ours. This scenario has the advantage of preserving unitarity within each universe separately, but it requires accepting a cosmology in which our universe is constantly generating disconnected offspring, which creates its own philosophical and physical difficulties. Among physicists working on quantum gravity today, the most widely held view is probably something like this. Complete evaporation occurs, information is preserved, and the mechanism by which information escapes is encoded in subtle quantum correlations in the Hawking radiation that are currently beyond our ability to calculate fully, but which follow from a correct theory of quantum gravity that we do not yet have. This view is supported by the page curve calculations and the holographic duality results that have accumulated over the last 2 decades. It is the view that is most consistent with the principles of both quantum mechanics and thermodynamics. And it is the view that makes the story of the black hole most complete, most closed, most thoroughly followed through. In this view, what remains after the black hole is gone is not a remnant and not a baby universe. What remains is the Hawking radiation, spreading outward at the speed of light, increasingly diluted, cooling as the universe expands, but carrying in the entanglement structure of its particles a complete record of everything that was ever absorbed. Not a record that could be read by any practical device. Not a record that any civilization could extract and decode, but a record that exists, a physical encoding of the past that is not erased, not overwritten, not lost. Just spread so thin that reading it would require a computational effort that makes the evaporation timescale look brief. The universe's memory is perfect, but its handwriting is illegible. Everything is there. Nothing was destroyed. The past is preserved in the radiation the way a message might be preserved in a bottle that has drifted to the bottom of the deepest ocean, intact in principle, effectively inaccessible in practice, but there. That is what remains, not the black hole, not a remnant. Just the radiation, and in the radiation, everything. There is something quietly comforting in that picture. The black hole is gone, but nothing was lost. The universe received everything back. The information is there in the quantum correlations of particles that will continue to spread outward long after the black hole itself has vanished. The story that began with a collapsing star, with specific atoms in specific arrangements, is still told in a new language, written in the language of Hawking radiation correlations, spreading across the universe at the speed of light, part of the thermal history of everything. What remains in the end is not nothing. It is not a remnant. It is the universe itself, changed by the black hole's existence, enriched by its evaporation, carrying the record. The black hole is gone, but its biography is permanently written into the fabric of the universe's quantum state. That is a kind of immortality, not the immortality of persistence, the immortality of having been, of having mattered, of having contributed to the state of everything that comes after. The black hole lasted longer than anything, and then it gave everything back. And the universe, patient and vast and remembering, carries it all forward. Sleep on that. The flash is over. The horizon is gone. The spacetime is flat. And somewhere out there, spreading at the speed of light, is everything the black hole ever was. Still there. Still part of the universe. Just different now. Just changed, but not gone. We have followed the physics all the way through. From the birth in a collapsing star, through the sealed geometry of the event horizon, through the quantum vacuum and the origin of Hawking radiation, through the thermodynamics and the information paradox, through the long, patient wait of the evaporation, through the final stages and the last second and the question of what remains. The physical story is told. Now it is time to do something different. Now it is time to sit with what all of this means, not in the language of equations or physical processes, but in the language of meaning, of what this story tells us about the nature of things, about power and impermanence, about patience and release, about the relationship between what is vast and what is lasting. Because stories about the physical universe are never only about the physical universe. They are always also about us. The universe does not have purposes or intentions. It does not arrange itself to communicate lessons, but the patterns it contains, the shapes of its processes, can resonate with patterns in human experience in ways that are worth taking seriously. And the story of the black hole is one of the most resonant patterns in all of physics. Let us start with what is perhaps the most obvious theme, the theme of power and permanence, and the universe's refusal to connect the two in the way we instinctively expect. We are built as thinking beings who evolved in a world of predators and limited resources to associate power with permanence. The strong things last. The dominant things endure. The largest structures in the environment are the most stable. Mountains outlast anthills because mountains are stronger. Rivers carve canyons because water is persistent. In the human world, this intuition is reinforced at every turn. Powerful empires are assumed to be enduring. Powerful institutions are assumed to be stable. The most massive and energetic things in our experience tend to be the things that change most slowly and persist longest. And then we encounter black holes, and the universe quietly dismantles this assumption with mathematical precision. In general relativity, black holes appeared to be the ultimate expression of permanence. They were the mountains of spacetime. Once formed, they could only grow. They were literally sealed off from the flow of time that affects everything else. They seemed to offer a kind of cold, dark immortality, a way for matter to exit the cycle of change and become a permanent feature of the geometry. But quantum mechanics says otherwise. Quantum mechanics says that even the most powerful gravitational trap is subject to the same thermodynamic laws as a cup of coffee. It says that power does not equal permanence. It says that everything that is concentrated must eventually disperse. The black hole, for all its terrifying strength, for all its ability to crush stars and swallow light, is not an exception to the rules of change. It is just a very slow participant in them. There is a deep humility in this. If even a black hole, the most absolute structure we know, eventually gives way to the flickering fluctuations of the quantum vacuum, then nothing in our experience can claim exemption. The universe does not allow for true stasis. It does not allow for permanent hoarding of energy or information. It insists on the flow. It insists that everything, regardless of how massive or how sealed, eventually participates in the great return. The second theme is patience. We have spoken about it throughout the story, but it is worth sitting with it now as a quality of the universe itself. The timescales we have discussed, 10 to the 67 years, 10 to the 100 years, are so far beyond human experience that they feel like abstractions. But they are not abstractions. They are the actual timing of the universe's evolution. And they tell us that the universe is a place where processes can take a very long time to arrive at their conclusion. We tend to judge the significance of events by their speed or their immediate impact. We are drawn to the explosions, the collapses, the dramatic shifts, but the majority of the universe's story is written in the long, dark middle. It is written in the patient evaporation of black holes. It is written in the quiet cooling of space. It is written in processes that happen so slowly they are invisible to any observer with a human lifespan. This suggests that the universe has a different relationship with time than we do. It suggests that for the universe, the long wait is not a delay or an interruption. It is the work itself. The patience of the black hole is not a state of waiting for something else to happen. It is the mode of its existence. It is the way it expresses its relationship to the laws of physics. The black hole is the most powerful, most dominant, most absolute structure in the known universe. Its gravity is stronger than any other force. Its boundary is more absolute than any other boundary. Nothing escapes it. Not matter, not light, not information, and classical physics provides no mechanism for its dissolution. It is, in classical terms, perfectly permanent, immortal, eternal. If any structure in the universe deserves to last forever, it is the black hole. By the intuition we evolved with, by the instinct we bring to questions of power and endurance, the black hole should be the last thing standing, the final structure, the permanent fixture. And it is, in a relative sense, the last thing standing. It outlasts the stars by factors of 10 to the 50 or more. It outlasts the atoms by factors of 10 to the 27 or more. It outlasts everything that ordinary matter can build or sustain. And in that sense, the intuition is honored. Power does translate into a kind of longevity that dwarfs everything else, but not into immortality. That is the key. That is what the mathematics of Hawking radiation insists upon against all expectation. The black hole is not immortal. Its power, its mass, is the very thing that creates its temperature through the inverse relationship that Hawking discovered. And its temperature, however low, means radiation, and radiation means mass loss. And mass loss carried far enough means death. The power is not a protection against the end. It is the mechanism of the end. The more massive the black hole, the colder it is, but coldness is not immortality. It is only a very, very long delay. There is something deeply humbling in this, and something deeply clarifying. Power does not confer permanence. Scale does not confer eternity. The universe does not have a category of things that last forever simply because they are large or strong or dominant. The category of forever is not available to physical structures. Every structure that exists within time is subject to time. Every arrangement of matter and energy that depends on specific conditions will eventually find those conditions have changed. Every sealed system will eventually, given enough time, open. The universe's arithmetic does not include true infinity as an available lifespan for physical structures. The black hole teaches this lesson more clearly than anything else can. Because if you believe that power and permanence were linked, if you were looking for the physical structure that deserved, on the basis of its power, to be immortal, you would choose the black hole. And the black hole turns out to be mortal, extremely long-lived, but mortal. The lesson is not that the universe is cruel or indifferent to power. The lesson is that the universe simply does not work that way. Permanence is not a reward for power. Duration is not a measure of dominance. The black hole will outlast everything else, and then it too will go. This is not a sad conclusion. It is, if anything, a liberating one. Because if even the most powerful thing cannot buy immortality, if even the black hole must eventually dissolve, then the question of what lasts is not about finding the most powerful thing. It is about something else entirely. And what that something else is, what does persist, what does carry forward, turns out to be the information, the pattern, the record, not the structure, but the story that the structure wrote as it lived and died. The universe remembers. Not the black hole, but what the black hole did. Not the power, but the history. There is a human parallel here, and I will offer it gently, because parallels between physics and human experience can be forced or false. But this one seems honest. We too are subject to the same disconnection between power and permanence. The things we build for permanence, institutions, empires, monuments, are not the things that last in the deepest sense. What lasts is more like information, more like pattern, the ideas that changed how people thought, the care that shaped a life or a generation, the acts that rippled outward into the lives of others and were carried forward in behavior and in love, and in the ways people treated one another. Not the stone, but the story the stone told about the people who quarried it and placed it and lived beside it. The black hole gives everything back in the form of radiation. The information persists in correlation spread across the universe. The structure is gone, but the story remains. If there is a template here for how to think about human life, about what we build and what we leave, it might be this. The structures we construct for permanence are not what persists. What persists is the information, the effect, the change in the state of everything that came after. The black hole evaporates completely and leaves the universe changed. Not by its continuing presence, but by the fact of its having been there, by the Hawking radiation it emitted, by the information encoded in that radiation, by the way it altered the thermal history of the universe it passed through. That is the permanence available to finite things, not the permanence of staying, the permanence of having been and having mattered and having changed the state of what comes after. The universe keeps a perfect record of everything that has happened. Every quantum of Hawking radiation carries that record forward. The black hole does not survive its own death, but its effect on the universe is, in the strictest physical sense, permanent. Rest with that thought. Power does not buy immortality, but nothing is lost. The record persists. The pattern continues. The universe remembers everything. And in a universe that remembers everything, nothing that happens is ever truly gone. That is what the black hole's death teaches us about power and permanence. And it is, quietly, one of the most reassuring things physics has ever said. We have sat with the theme of power and permanence, with the universe's refusal to grant immortality to even its most dominant structures, and with the reassuring idea that what persists is not the structure but the record, not the thing but the effect it had on everything around it. Now let us turn to the second great philosophical thread that runs through this story, the one that is perhaps more intimate, more applicable to the texture of daily life, and in some ways more surprising. The theme of intensity followed by infinite patience. Think about the biography of the black hole again, but this time not as a story about physics. Think about it as a story about the rhythm of existence. It begins in an instant of tremendous violence, a supernova, a collapse, a moment of such concentrated energy that nothing in the universe can match it. The birth of a black hole is about as intense as anything physics can describe. Pressures beyond any comparable, temperatures beyond any comparable, energies released in seconds that dwarf the lifetime output of ordinary stars. It is a beginning that announces itself with everything it has. And then, for timescales that make the word long meaningless, almost nothing happens. The black hole sits. It is cold. It is dark. It radiates so feebly that no instrument we could build could detect it. The universe changes around it dramatically. First the brilliant era of stars, then the cooling, then the dispersal, then the dissolution of matter itself. And the black hole remains, barely altered, patient beyond any concept of patience. For 10 to the 67 years or 10 to the 94 years, it simply is. Not becoming, not transforming, not moving toward anything in any perceptible way, just existing with its sealed geometry and its imperceptible leak and its temperature barely above absolute zero. And then at the very end, another intensity, rising temperature, accelerating evaporation, diversifying radiation. And finally, the last second, the flash, the most energetic event in the vicinity of that piece of space for all the time since the stars went out. Intense beginning, infinite patience, intense ending. That is the arc. What does this rhythm teach us? Or rather, since the universe does not teach, what does this rhythm resonate with in the experience of conscious beings who also live in time? There is a quality to intense beginnings that is familiar. Starting something is often the most energetic part. The formation of a new relationship, the beginning of a new project, the birth of a child, the start of a journey. Beginnings often arrive with a concentration of energy that is not sustainable over long periods. The intensity of beginnings is real and valuable. It generates momentum. It breaks inertia. It commits the system to a new configuration. But it is not a steady state. It cannot be maintained. The supernova cannot burn forever. What follows the intense beginning, the long middle, is often the part we find most difficult to inhabit. The long middle is where the work is done, where the structure proves itself, where the patience required to sustain something over time reveals whether the beginning was a genuine commitment or just a burst of energy that fades. The long middle is where most things fail, not because they were wrong to begin, but because the intensity of beginning could not be translated into the patience required to sustain. The black hole is extraordinary not because it began intensely. Lots of things begin intensely. It is extraordinary because the intensity of its beginning was converted so completely and so thoroughly into patience. The collapsed star, that released more energy in seconds than most stars produce in billions of years, became the coldest, most patient object in the universe. Nothing was lost. The same mass that generated the supernova became the mass of the black hole, but now it expressed itself not as explosive release but as sealed, patient gravity. The intensity was not wasted. It was transformed, converted into a different mode of being, stored, and then at the end released again. The patience was not the final state. The patience was the middle state, the long holding, the enormous reservoir of potential maintained across incomprehensible time. And at the end, when the conditions were finally right, when the mass had dropped far enough, when the temperature had risen far enough, when the moment had arrived, the stored potential was released one last time in that final second of intensity. Intensity, patience, intensity. Beginning, middle, end. The black hole lives this rhythm more thoroughly, more completely, more absolutely than anything else in the universe. And in living it so absolutely, it illuminates something about the nature of existence that is not obvious from inside the middle of our own lives. We spend a great deal of our lives in the middle, not at the intense beginning of something and not at the final resolution, but in the long work of sustaining what was begun and moving toward what will eventually end. And the middle can feel like nothing is happening. The middle can feel like the intensity was a mistake, like maybe things were not supposed to go the way they seemed to promise at the start, like the gap between the energy of the beginning and the quiet of the middle represents some kind of failure or loss. The black hole says otherwise. The middle is not a failure of the beginning. The middle is the transformation of the beginning. The intensity has been converted into something else, not dissipated, not lost, but changed in form, stored as potential, held in the sealed geometry of a patient, dark, barely radiating sphere in space. The long middle of the black hole's life is not a period of inactivity. It is a period of being, a period of holding the shape that the intense beginning created, and radiating, imperceptibly but continuously, the slow output that will eventually add up to everything. There is patience in that picture that is worth recognizing, not the passive patience of waiting for something to happen, but the active patience of sustaining a form across time, of continuing to be what you are through all the changes in the environment around you, of trusting that the slow, barely perceptible output is still output, that the almost unmeasurable change is still change, that the direction towards zero is still a direction, even when it cannot be seen. The black hole does not doubt its direction. It cannot, but we can borrow the image and let it say something to the part of us that finds the long middle difficult. The intensity at the beginning was real. The patience in the middle is real. The release at the end will be real. The arc is complete. Nothing is wasted. Nothing is lost. The long quiet is part of the story, not a departure from it. There is also something in the final burst that deserves separate attention. The last second of a black hole's life, that flash of energy after 10 to the 67 years of near invisibility, is the most dramatic reversal of character in physics. The coldest thing becomes the hottest. The darkest thing becomes the brightest. The most patient thing becomes the most urgent. In 1 second, it emits what it has been gradually approaching for all of cosmic time. The contrast is absolute. And yet it is not a contradiction. The final burst is not a betrayal of the patience that preceded it. It is the fulfillment of it. Every quantum emitted over all those years was pointing toward this. The The slow descent of the mass, the slow rise of the temperature, the slow diversification of the radiation, all of it was building, imperceptibly but inevitably, toward the moment when the last of the held potential was released. The patience was not the opposite of the intensity. The patience was the approach to the intensity. The long, quiet middle was the long approach to the brief, bright end. And in that approach, in those 10 to the 67 years of almost perfect quiet, something was happening that we should not pass over without recognizing. The Hawking radiation was being emitted, continuously, at every moment, so feebly as to be undetectable, but continuously. The black hole was not doing nothing during the long middle. It was doing the most patient possible version of its final act, emitting, slowly, quantum by quantum, the radiation that would eventually total its entire mass. The final second was not the only time it was giving back. The final second was just the last and most concentrated expression of a giving back that had been ongoing since the moment of formation. The intensity was continuous. It was just so quiet for so long that it required a cosmic timescale to hear it accumulate into something audible. That, too, is worth sitting with. The quiet output that feels like nothing, the barely detectable effort that seems too small to matter, may be, over time, the majority of the work. The visible intensity at the end is real and important, but the invisible patience of the middle is where most of the transformation actually happens. The black hole spent almost all of its energy, almost all of its evaporation in the long, imperceptible middle. The final burst is dramatic, but the long quiet was substantial. Let your body settle a little more into where it rests. Let the thought of intensity giving way to patience and patience giving way to release settle into your breathing. The black hole lived that rhythm completely. The universe provided the time and the conditions for it to live that rhythm. And somehow out of that rhythm, from that violent birth and that incomprehensible patience and that brief, brilliant ending, everything that was there was returned to the universe. Nothing held back, nothing kept, everything given. That is the second great theme of this story. Intensity and patience are not opposites. They are phases. They follow one another. They complete one another. And the arc that runs through both of them, from the supernova birth to the final flash, is one of the most complete arcs in all of physics. Rest in that. The patience is real. The release will come. And the arc, however long it takes to complete, is always moving toward its end. We have spent much of our time following a simplified version of the black hole, what physicists call a Schwarzschild black hole, a perfectly spherical, non-rotating, electrically neutral object. This idealization is useful and honest for the purpose of understanding the fundamental physics of horizons and evaporation. But the universe does not produce idealized objects. The universe produces messy, rotating, complicated things. And the black holes that actually form in nature are almost all rotating. The stars that collapsed to form them were rotating. And when angular momentum is conserved through the collapse, the resulting black hole inherits that rotation and concentrates it into an extraordinarily small volume. The result is a rotating black hole, what physicists call a Kerr black hole, and it has properties that are richer and stranger than its non-rotating cousin. The difference between a rotating and a non-rotating black hole is not merely a detail. Rotation changes the geometry of spacetime in ways that have profound consequences for everything near the black hole. The most important of these consequences is a phenomenon called frame dragging. A rotating black hole does not merely curve spacetime. It drags spacetime around with it, literally pulling the fabric of space in the direction of its rotation. The way a spinning ball bearing in thick oil drags the surrounding oil around with it. Anything near a rotating black hole is pulled in the direction of rotation, not by any conventional force, but by the geometry of spacetime itself being dragged around. This frame dragging creates a region outside the event horizon called the ergosphere. The ergosphere is bounded on the outside by the stationary limit surface, the boundary within which it is impossible for any object to remain stationary with respect to distant space, even moving at the speed of light. Inside the stationary limit, everything must orbit in the direction of the black hole's rotation. You cannot hold still. The dragging of spacetime is so powerful that all futures are pulled around in the direction of rotation. The ergosphere is not inside the horizon. You can still escape from it, but inside it, you cannot remain motionless. The ergosphere has a fascinating implication that was worked out by Roger Penrose in 1969, years before Hawking discovered his radiation. Penrose showed that within the ergosphere, it is possible to extract energy from the rotating black hole. The mechanism works like this. An object falls into the ergosphere and splits into two pieces. One piece is engineered to have negative energy in the frame of the black hole, which is possible within the ergosphere because of the way the geometry works, and falls through the event horizon. The other piece, now with more energy than the original object had, escapes back out to infinity. The energy came from the rotation of the black hole itself, which slows slightly as a result. If this process were repeated many times, the rotation of the black hole could be reduced, extracting energy from the rotational energy of the spacetime geometry. This is called the Penrose process, and while it is not practically achievable with any technology we can imagine, it is theoretically real. It demonstrates that rotating black holes have a reservoir of extractable energy in their rotation, energy that is, in principle, accessible from outside the horizon. This is different from the evaporation we have been discussing, which involves quantum effects and the Hawking temperature, but it is related in an important way. When Hawking radiation was discovered, it was shown that rotating black holes radiate preferentially in a way that reduces their angular momentum, that the Hawking radiation carries away not just energy, but also angular momentum, so that over the course of its evaporation, a rotating black hole spins down as well as loses mass. By the time a rotating black hole is near the end of its evaporation, it has lost almost all of its angular momentum to radiation and has become, to a very good approximation, a Schwarzschild black hole. The rotation, which was such a prominent feature of its early life, is radiated away long before the mass is gone. This is a beautiful detail in the story. The rotating black hole that forms in the collapse of a spinning star is, in its early life, more complex, more dynamic, more energetic than a non-rotating one. The ergosphere gives it additional structure. The frame dragging gives it additional effects on the surrounding spacetime. The Penrose process gives it additional ways to interact with and influence its environment. The rotating black hole is, in some sense, the more interesting object. And yet, over the course of its immense evaporation, it gradually loses that complexity. It sheds its angular momentum into the universe, the way a spinning top gradually slows as it loses energy to friction, and eventually becomes simple, spherically symmetric and quiet. Complexity at birth, simplicity at death. The evaporation is not only a loss of mass, it is a simplification, a reduction to essentials. By the time the final burst comes, the black hole has become as simple as a black hole can be. Electrically charged black holes follow a similar arc. The full family of black hole solutions in general relativity, described by mass, spin, and electric charge, are known as the Kerr-Newman family. In practice, astrophysical black holes are not expected to carry significant net electric charge, because any charge imbalance would be quickly neutralized by attracting opposite charges from the surrounding plasma. But in principle, a charged black hole is a physically valid object, with additional structure near the horizon, an electric field extending outward to infinity, and a slightly modified version of the Hawking radiation that preferentially emits charged particles and reduces the charge over time. Like rotation, charge is radiated away over the course of evaporation. By the end, what began as a Kerr-Newman black hole has become, through the gradual shedding of both rotation and charge, a simple, uncharged, non-rotating Schwarzschild object. The complexity it was born with has been returned to the universe. The final flash is the flash of the simplest possible black hole. This tendency of the evaporation to simplify the black hole, to reduce it from a complex, rotating, potentially charged object to a simple, spherical, uncharged one, is consistent with the broader theme of the story. The beginning is complex and violent. The middle is a gradual shedding of complexity. The end is simple, brief, and complete. The arc moves from the complicated to the essential, from the many-featured to the one-featured, from the rich to the irreducible, and then from the irreducible to nothing. The simplification precedes the dissolution. Before a thing can be fully released, it must be fully simplified. The rotating black hole must first become a Schwarzschild black hole, and then the Schwarzschild black hole must become a Planck mass object, and then the Planck mass object must become nothing. Each step is a letting go of something that seemed essential. Each step reduces the black hole to something more fundamental, until there is nothing left to reduce, and the process completes. There is a theme here that goes beyond physics. The arc from complexity to simplicity to dissolution, the gradual shedding of what seemed essential, the reduction to the irreducible and then beyond, is a pattern that appears in other contexts. Things that are complicated and multifaceted in their full vigor become simpler as they near their end. The complexity that was necessary for the full life of the thing is gradually returned to the environment from which it was drawn. What remains is the essential, and then, eventually, even that is released. For a black hole, the essential is mass. The spin and the charge are shed first, and then the mass itself goes, quantum by quantum, in the Hawking radiation. For other things, we need not specify what. The process of shedding complexity may also be a feature of endings, and there may be a grace in that simplification, a clarity that complex beginnings cannot have, a cleanness that comes only when the inessential has been returned, and what remains is only what was always most fundamental. The rotating black hole, with its ergosphere and its frame dragging and its Penrose process and its rich angular momentum structure, will eventually become a simple sphere of spacetime curvature, and then nothing. But on its way to nothing, it will have participated fully in the universe it inhabited. It will have shaped the orbits of stars and gas around it. It will have generated relativistic jets of plasma that illuminated galaxy-scale regions. It will have grown by merger with other black holes, each merger sending gravitational waves rippling across spacetime at the speed of light. It will have had a biography of interactions and effects that extended far beyond the sealed geometry of its horizon. And then it will have shed all of that, spin, charge, interaction, and become simple, and then become nothing. The biography will be over. The radiation will carry it all. Let the image of the rotating black hole settle, spacetime dragging around it. The ergosphere as a region of concentrated geometric activity, the slow spinning down over incomprehensible timescales, the gradual approach to the simple, the essential, the irreducible, and then the final simplicity of the last moments. No rotation, no charge, just mass, and then not even that, just radiation, just the universe remembering everything, holding nothing back. That is the rotating black hole, rich at birth, patient in its middle age, simple at the end, and then gone, giving everything it ever had back to the space it once dominated. We have followed the stellar and supermassive black holes that dominate astrophysical discussions. But there is another class of black hole that deserves its own attention in this story, one that has never been confirmed by observation, but is predicted by the physics of the early universe, a class that is, in terms of evaporation, far more dramatic than any object we have yet discussed. These are the primordial black holes, objects that may have formed in the first fraction of a second after the Big Bang, and which, if they existed with the right range of masses, may already be evaporating, or may already be gone. The early universe was an extraordinarily dense and energetic place. In the first moments after the Big Bang, the density of matter and radiation was so high that small regions could, in principle, collapse under their own gravity to form black holes. This does not require a dying star. It does not require a supernova. It requires only that the density fluctuations in the early universe were large enough in some regions that those regions collapsed directly from the hot, dense plasma of the early cosmos. The black holes that would form this way are called primordial black holes, and they could, in principle, span an enormous range of masses, from far less than a gram to millions of solar masses, depending on the scale of the density fluctuation that formed them and the moment in cosmic history when the formation occurred. The most immediately interesting primordial black holes, from the perspective of Hawking evaporation, are the ones with masses small enough that they would have evaporated by now, or would be evaporating right now, or would be in their final stages in the near future. And the mass that determines whether a black hole has a current age comparable to the universe's age is about 10 to the 11 kilograms, roughly the mass of a moderate-sized mountain. A primordial black hole formed with this mass would have a Hawking evaporation timescale of roughly the current age of the universe. It would be in its final stages now. It would be emitting Hawking radiation at temperatures of around 1 billion Kelvin, producing gamma rays. This is why primordial black holes of this mass are of intense interest to observational astronomers. If they exist, their final evaporation would produce gamma ray bursts of a specific character, a rising signal over the final months, culminating in a brief, intense burst as the last of the mass is released. The specific spectrum and time profile of this signal would be distinctive, different from other astrophysical gamma ray sources, and could, in principle, be identified by gamma ray observatories. So far, no confirmed primordial black hole evaporation has been detected. But the search continues, and its absence so far has allowed physicists to constrain what fraction of the universe's dark matter could consist of primordial black holes of various masses, the bounds being derived from the fact that if too many of them existed in the right mass range, we would have detected their gamma ray signals by now. The primordial black holes that formed with larger masses, those that are not yet evaporating or are evaporating on much longer timescales, are even more intriguing from a cosmological perspective. There has been serious discussion in the physics community about whether primordial black holes could account for some or all of the dark matter in the universe. Dark matter is the invisible mass that makes up roughly 27% of the universe's total energy density. That holds galaxies together. That shapes the large-scale structure of the cosmic web. But that does not emit or absorb light and has not been identified with any known particle. If primordial black holes in certain mass ranges formed in sufficient numbers in the early universe, they could contribute to or entirely account for this dark matter. The gravitational wave observations from the LIGO and Virgo collaborations have added fuel to this discussion. Several of the black hole mergers detected by these instruments have involved black holes with masses in ranges that are somewhat unexpected from stellar evolution alone, suggesting to some researchers that primordial black holes of these masses might exist. The debate is ongoing and has not reached consensus, but it has reinvigorated interest in the primordial black hole hypothesis in a way that seemed unlikely before gravitational wave astronomy was possible. For our story, the significance of primordial black holes is this: they demonstrate that the range of black hole masses, and therefore the range of black hole lifetimes, is potentially far wider than we might have assumed if we only thought about the stellar collapse origin. The evaporation story is not just a story about objects that will die in 10 to the 67 years. It may also be a story about objects that are dying right now, or that died long ago. Objects formed in the first second of cosmic history, evaporating in the last moments of their brief lives as the universe around them is still relatively young. If primordial black holes of just the right mass formed in the early universe, their evaporation today would be the first Hawking radiation ever detected, the first direct confirmation of one of the most important theoretical predictions in the history of physics. Detecting even a single such event would be a landmark. It would not only confirm Hawking radiation, it would provide evidence for the primordial black hole hypothesis. It would constrain models of the early universe. It would tell us something about the density fluctuations in the first moments of cosmic time. It would be, in short, one of the most important observational discoveries in the history of science. And there is something beautiful in the thought that if such an event happened, if a primordial black hole that formed in the first second of the universe finished its evaporation today or tomorrow or next year, it would complete a story that spans essentially the entire history of the cosmos. Born in the first fraction of a second, patiently radiating for 14 billion years, most of that time at temperatures so low as to be undetectable, and then, finally, in the current era, reaching its final moments, a lifespan that equals the current age of the universe, an existence that encompasses essentially all of cosmic history that we know about. That is a kind of completeness that is almost impossible to fully absorb. A primordial black hole evaporating today has been there through all of it. Through the formation of the first stars and galaxies, through the long stellar era and the gradual cooling, through the emergence of chemistry and planets and life, through all of human history, which occupies a fraction of the last instant of the black hole's 14 billion year lifetime, through the invention of physics and the development of general relativity and quantum mechanics, which are the very tools that allow us to understand what the black hole has been doing all along, and now, perhaps, ending. Completing the arc, releasing the last of its mass in a burst that the very species that worked out the physics of its evaporation might be positioned to detect. There is a poetry in that coincidence that the universe did not plan but that we can recognize. The physicist who worked out the mathematics of black hole evaporation, Stephen Hawking, did so in 1974, and in the same era, the first systematic searches for primordial black holes were being considered. If a primordial black hole is evaporating now, it is doing so precisely when the humans who figured out the mechanism are still alive to look. Not because the universe planned it that way. The universe does not plan. But because the same conditions that allow a technological species to develop and ask questions about physics, a long, stable, stelliferous era with reliable star energy and planetary chemistry, are also the conditions under which 14 billion-year primordial black holes would be completing their evaporation. The timescales coincide. Whether that coincidence is profound or accidental is a question each person must answer for themselves. For the story we are telling tonight, the primordial black hole adds a dimension that the astrophysical black holes could not. It adds the dimension of urgency, the possibility that the evaporation we have been discussing as a future event, a distant future event, an incomprehensibly distant future event, is actually a current event, is happening now, is emitting gamma rays that are perhaps reaching detectors on Earth tonight, not the 10 to the 67-year story. A 14 billion-year story, still vast, still beyond human scales of lived experience, but finite in a way that connects to the observable present. Let that settle in alongside everything else, the small ones first, the primordial objects that formed when the universe was young, racing toward their end now or already done, the stellar ones patient for 10 to the 67 years, the supermassive ones patient for 10 to the 94 years, all of them on the same road. All of them heading to the same destination, just traveling at very different speeds. The universe produces black holes in a range of sizes, and it gives each one exactly as much time as its mass entitles it to, no more and no less. The arithmetic is fair in its way. Mass determines temperature, temperature determines evaporation rate determines lifespan. The equation is the same for all of them. Only the input, the mass, varies. And from that one variable, that single number, the entire biography follows. How long the patience lasts, when the final burst comes, what the flash looks like. The equation does not discriminate. It applies equally to the primordial and the stellar and the supermassive. The same physics, the same arc, the same destination. Just different timescales, just different degrees of patience, but the same story. That is a kind of universality that is worth appreciating as you drift toward sleep. The same laws that govern a primordial black hole evaporating today also govern the supermassive monster that will not evaporate for 10 to the 94 years. The same Hawking temperature formula, the same evaporation equation, the same final burst. The universe applies its laws without exception and without preference. And in that consistent application, across every black hole in every galaxy at every epoch of cosmic history, the same story is told, again and again, at different speeds. The slow death of black holes is not one story. It is the same story told 10 to the however many times, each telling complete in itself, each one unique in its details, but all of them following the same arc, from intense birth to patient middle to final release, all of them eventually done. Before we arrive at the final reflections, before we begin to close this long, slow journey and bring it back to the quiet room you are resting in now, let us spend one part thinking about the black hole not in isolation, but in relation to the universe it inhabits and shapes. Because the slow death of a black hole is not a private affair. The black hole is not a sealed room with no windows. It is a participant in the cosmos around it. It shapes its environment in ways that leave marks long after it is gone. The most dramatic way a black hole influences its environment is through the jets. Rotating black holes that are actively feeding, that have surrounding disks of infalling gas and dust, often produce two narrow beams of plasma and radiation that shoot out along the rotation axis, perpendicular to the accretion disk, at speeds approaching the speed of light. These relativistic jets can extend for thousands or even millions of light years into the surrounding space. They are among the largest coherent structures in the observable universe, and they carry an enormous amount of energy, enough to heat and push around the gas in entire galaxy clusters. These jets are powered by the interaction of the rotating black hole's magnetic field with the infalling matter and the ergosphere we discussed in the last part. The exact mechanism is still a subject of active research, but the outcome is well established observationally. Jets that illuminate their surroundings, carve cavities in the hot gas that fills galaxy clusters, and regulate the rate at which new stars form in their host galaxies. Without these jets, without this feedback from the central black hole, galaxies would form stars much more rapidly than they actually do, would exhaust their gas supply too quickly, would produce stellar populations that look nothing like the ones we observe. The supermassive black holes at the centers of galaxies are not just passive residents. They are active regulators, throttling the star formation of their host, shaping the evolution of the galaxy on cosmic timescales. This is a remarkable thing to appreciate. The black hole, which is, in some ways, the ultimate passive object, the thing that only takes in and never gives out in the classical picture, is actually, in the real universe, one of the most energetically influential objects there is. It influences through its jets, through its gravitational effects on surrounding matter, through its role in galaxy mergers. Because when two galaxies collide and merge, their central black holes will eventually spiral together and merge as well. And that merger releases gravitational waves of extraordinary power, detectable across vast distances. The mergers of supermassive black holes are expected to be the most powerful gravitational wave sources in the universe, and their signals should be detectable by future gravitational wave observatories, sensitive to the very low frequencies that such massive mergers produce. The mergers themselves are worth imagining. Two supermassive black holes, each containing millions or billions of solar masses, each with their own event horizon, their own ergosphere, their own frame dragging effect on surrounding spacetime, approaching each other over millions of years as the surrounding gas and stars slowly drain energy from their mutual orbit. And then finally, close enough to be in each other's strong field regime, the final inspiral, a dance of two sealed regions of spacetime, and the merger, two horizons becoming one, a single, larger black hole left behind, and radiating in the final moments of the merger more power in gravitational waves than all the stars in the observable universe radiate in light. For a brief moment, seconds or minutes, the merger outshines everything in the cosmos in the gravitational wave band. The merged black hole then rings down, oscillating and settling into the Kerr geometry appropriate to its new mass and spin, emitting gravitational waves in a characteristic pattern called quasi-normal modes, and then settling into the quiet, patient existence of a more massive Kerr black hole. Larger, more massive, with a longer evaporation time. The merger has extended the black hole's lifespan, not by a vast amount, but by the cube of the mass ratio. Throughout the history of the universe, black holes have been merging and growing in this way. The supermassive black holes that sit at the centers of galaxies today are the products of many mergers, of many generations of infall and coalescence, each growth step extending the evaporation timescale. The most massive ones, those with billions of solar masses, grew through the most mergers, the most feeding, the most accumulation. And they will live the longest, not because they are somehow more deserving, but because the mathematics of mass cubed is unambiguous. Every solar mass added to a black hole through feeding or merger extends its evaporation time by roughly the cube of the proportional mass increase. But feeding also stops. After the stelliferous era ends, after the last stars burn out and no new ones form, the accretion of matter onto black holes will cease. The reservoirs of gas that fed the accretion disks will be exhausted. The mergers will have already occurred. The galaxy clusters will have already coalesced. The last major gravitational interactions will have settled. And the black holes will sit, alone in their dark galaxies, with nothing left to absorb, radiating their Hawking temperatures into an increasingly dark and empty universe. From that moment, whenever it comes in the future, the black holes are on a one-way path. No more growth. Only evaporation. The mass that accumulated over the active feeding period. The mass from the birth supernova and all subsequent mergers and all the gas and dust that fell in over billions of years. That is now the total inventory. And from that inventory, the Hawking radiation will slowly, imperceptibly withdraw, quantum by quantum, until the inventory is zero. There is something in this picture that is worth dwelling on. The black hole spent its active phase accumulating, growing, feeding, becoming more massive, extending its own eventual lifespan. Every merger, every meal added to the mass and pushed the end further into the future. The black hole was, in a sense, delaying its own death by growing. Not consciously, not with intention, because black holes have no intentions, but effectively. The growth period was also a life extension period. And then the growth stopped. And from that moment, the direction reversed. Every quantum emitted is a step closer to the end rather than away from it. The same mass that was accumulated over billions of years of active growth will be returned over timescales that make those billions of years look like an eye blink. The accumulation was fast by cosmic standards. The return is incomprehensibly slow, but they are the inverse of each other, gathering and releasing, the two halves of a transaction with the universe. The gathering was dramatic. The release is quiet. The gathering involved jets and mergers and gravitational waves that shook the fabric of spacetime. The release involves a temperature barely above zero and radiation too faint to detect. The gathering was witnessed. Galaxies blazed with the light of active quasars when their central black holes were feeding heavily. Among the brightest objects in the observable universe, visible across billions of light years. The release will be unwitnessed. There will be no observers, no stars to illuminate, no planets to harbor life, no civilizations to operate telescopes. The final evaporation will happen in a universe so dark and empty that the flash, though the most energetic local event for vast stretches of time, will propagate into a void. That asymmetry between the witnessed gathering and the unwitnessed release is part of the poignancy of the story. The black hole accumulated its mass in a universe full of light and life and observers. It will release it in a universe empty of all three. The accumulation was public. The dissolution is private. The gathering was part of a universe that could appreciate it. The release will occur when there is nothing left to appreciate it, only spacetime itself, expanding and cooling, receiving the radiation without fanfare. Perhaps there is something important in that. The value of a process is not determined by whether it is witnessed. The completeness of a transaction is not diminished by the absence of an audience. The black hole gives back everything it accumulated in full with no residual, and it does so whether or not anyone is there to see it. The universe's accounting is not dependent on observation. It is not a performance. It is simply what happens. The release is as real as the gathering. The evaporation is as real as the formation. The end is as real as the beginning. And all of it, gathering and releasing, birth and death, formation and evaporation, is the story of the black hole's participation in the universe. That participation mattered, not because it was observed, because it happened, because the universe was different for it. Because the galaxies it regulated, the stars whose formation it throttled, the gravitational waves it generated in mergers, the Hawking radiation it emitted over incomprehensible timescales. All of that is part of the universe's history, permanently, unchangeably. The past is the one thing in the universe that cannot be altered, and the black hole's past, its entire biography, is there, woven into the fabric of what the universe became and will continue to become. That is the black hole's legacy. Not a monument, not a remnant, a changed universe. A universe that is what it is, at least in part, because the black hole was there and did what black holes do. And the universe, patient and vast and remembering, carries that legacy forward. In the motion of stars, in the thermal history of the intergalactic medium, in the gravitational wave background that ripples through spacetime as a record of every merger that ever occurred, in all the subtle ways that what was continues to matter to what is. Rest with that. The black hole participated, and the universe is different for it. That is enough. We have arrived at the final parts of our journey. We have covered vast ground, from the supernova birth through the quantum vacuum, through thermodynamics and the information paradox, through the long, patient evaporation and the final second and the question of what remains, through rotating black holes and primordial objects and the role black holes play in shaping galaxies. We have followed a single thread, the slow death of black holes, and found that it connects to almost everything in physics, general relativity, quantum mechanics, thermodynamics, information theory, cosmology. The story of how black holes die turns out to be a story about how the universe works at its most fundamental level. Now let us sit with something that has been implicit in the whole story, but deserves to be made explicit. The death of a black hole is not the end of the universe. The universe continues long after the last black hole has evaporated. And what kind of universe that is, what persists after the most durable structures have dissolved, is worth thinking about because it puts the black hole's death in a context that is both humbling and strangely comforting. After the last black hole evaporates, after the final burst of the last and most massive supermassive black hole has propagated outward and diluted, what is left? By this point in cosmic history, somewhere around 10 to the 100 years or beyond, the universe is nearly unimaginably different from the one we inhabit. There is no ordinary matter. The protons have long since decayed. The white dwarfs and neutron stars that persisted into the degenerate era have dissolved. The last black holes are gone. What remains is a universe of photons, neutrinos, gravitons and electrons and positrons, the lightest possible particles, drifting in a space that is expanding and cooling. The density of these particles is so low, and the expansion so relentless, that even individual particles are separated by distances that dwarf the current observable universe. This is called the dark era by cosmologists who think about these timescales, and it is aptly named. There are no sources of light, there are no structures, there is no chemistry, there is no complexity of any kind. There is only the faintest possible hum of particles so dilute that the universe is, in the most practical sense, as close to empty as physics allows. And yet even here, even in this most diluted and featureless of all possible conditions, the universe is not quite nothing. The quantum vacuum continues to fluctuate. The laws of physics continue to apply. The expansion continues. Time continues. There are speculations at the very frontier of theoretical physics and cosmology about what might happen in this dark era. One is that random quantum fluctuations, acting over timescales that make the evaporation of black holes look brief, could occasionally produce, by sheer statistical chance, a random concentration of matter in a small region, a spontaneous ordering of the disordered. Such an event is called a Boltzmann brane, after the physicist Ludwig Boltzmann, who first worried about the possibility, a hypothetical spontaneous fluctuation into a state of high complexity. The idea is more of a philosophical problem than a prediction. It arises when you take the implications of statistical mechanics and eternal time to their logical extreme. And most physicists regard it as a sign that there is something conceptually incomplete about infinite time cosmology, rather than as a genuine physical prediction. But it illustrates the strangeness of what happens when you grant the universe enough time, and the laws of physics enough room to explore all their possibilities. Another speculation involves what happens to the expansion itself. In a universe dominated by dark energy, the accelerating expansion we currently observe, the expansion continues forever, growing faster and faster, until the space between any two particles is increasing at a rate faster than light can bridge. In this de Sitter universe, named after the Dutch physicist Willem de Sitter who first analyzed it, even the quantum vacuum has a non-zero temperature, a temperature associated with the acceleration of the expansion, analogous in some ways to the Hawking temperature. This temperature, called the Unruh de Sitter temperature, is extraordinarily low, far lower even than the Hawking temperature of the most massive black holes, but it is non-zero. The expanding universe itself radiates, very faintly, as a consequence of the quantum vacuum in accelerating spacetime. In the very distant future, after the last black hole has evaporated, the thermal properties of the universe will be dominated by this background temperature, the temperature of empty, expanding, dark energy-dominated space. The universe will be in a thermal state, in equilibrium with its own geometry, at a temperature so low it has no comparison in any process we know. And it will remain in this state, essentially forever, because this equilibrium has no further decay channel, no mechanism that allows it to cool further or change further. It is, in a very particular sense, the final state of the universe, as close to nothing as something can be while still being something, still governed by the laws of physics, still having a temperature, still fluctuating at the quantum level, but containing nothing recognizable as structure, nothing that could support complexity, nothing that could be called in any meaningful sense active. The black holes, those last, most durable structures, gave way to this. Their final burst was the last departure from this background, the last event of any consequence before the universe settled into its final equilibrium. And after their departure, the universe became what it will be essentially forever, a nearly featureless, nearly empty, slowly expanding, quantum fluctuating de Sitter space, the most enduring state of all, and the least interesting by human standards, and the most peaceful if peace can be attributed to a physical state. There is something in this picture that resonates with the idea of rest. The universe, after all its activity, after the Big Bang and the formation of structure and the stellar era, and the long decline and the black holes and their evaporation settles into a state of maximum entropy and minimum structure. It reaches the state that physicists call equilibrium, the state where nothing further can happen, where all the available energy has been distributed as uniformly as possible, where the temperature everywhere is as close to uniform as the laws of physics allow. This is sometimes called the heat death of the universe, a term that sounds dramatic but describes something that is, in physical terms, simply the endpoint of thermodynamic evolution. Everything that can happen has happened. Every gradient that could drive a process has been smoothed out. The universe is, in the deepest physical sense, at rest. The black holes were the last holdout against this rest. They were the last structures that maintained a gradient, a difference between the interior and the exterior, a sealed region of higher density in an otherwise increasingly uniform space. And when they evaporated, the last gradient dissolved. The universe became uniform. The universe came to rest. Whether that is a tragedy or a completion depends on how you look at it. From the perspective of the complexity and richness of the universe we currently inhabit, with its stars and galaxies and life and thought, the final uniformity looks like loss. Everything that made the universe interesting from our perspective was built on gradients, on differences, on the disequilibrium between hot and cold, between dense and sparse, between structured and unstructured. And the end of all gradients is the end of all of that. But from another perspective, the journey from the Big Bang to the heat death is a story of transformation, not of loss but of change, a complete arc that starts with the most extreme possible departure from equilibrium, the Big Bang itself, and ends with equilibrium, the final uniform state. The black holes were part of that arc. They were a stage in the transformation. And their evaporation was the final step, the last departure from the final state, the last transaction between structure and uniformity. They completed the work that the universe started. They were, in that sense, the universe's way of finishing what it began. The black hole's death is not a punctuation mark at the end of a sad story. It is the completion of a process that was always heading this way. The universe began out of equilibrium, densely packed, energetically rich, and it has been moving toward equilibrium ever since, building structures, burning stars, forming galaxies, creating life and thought, and then watching all of those things dissolve back into uniformity. The black holes are the last chapter of that process. Their evaporation is the final return to equilibrium. And the quiet, dark, nearly empty universe that follows is not a failure. It is the destination. The place the universe was always heading. The end of the story. And in that end there is something that the beginning did not have. Uniformity, equilibrium, the complete mixing of everything that was ever separate. All the information from every black hole, from every star, from every atom, from every quantum event since the Big Bang, is there, encoded in the correlations of the radiation, spread so thin as to be practically inaccessible but present in principle. The universe in its final state is, paradoxically, the most information-rich state it has ever been in, because all the information from all of its history is there, distributed across all of space, even if no intelligence will ever be able to read it. The universe remembers everything, even at the end, even in the dark, even in the quiet after the last black hole has gone. The memory is there, in the correlations, in the quantum state of the radiation. In the thermal history written into the fabric of the universe itself, everything that happened, every star that burned, every galaxy that formed, every life that lived, every black hole that formed and evaporated is part of the final state, part of the memory. That is the universe after the black holes, dark, quiet, nearly empty, at rest. and holding in the correlations of its quantum state the complete history of everything that ever was. Rest now. Let the image of that final quiet settle, not as loss, as completion, as the universe after all its work finally at rest. We have arrived at the final parts of our journey. We have followed the black hole from birth to death, and we have followed the universe from its current brilliant age to its final quiet. Now let us spend the last sections returning from those vast distances to something closer, to the room you are in right now, to the body that is resting, to the breath that is moving in and out, to the particular moment in cosmic history that you occupy. Because the story of the black hole's slow death is not only a story about physics, it is a story that reaches back and touches the way we think about our own lives, not by making our lives seem small, though in the arithmetic of timescales they are, but by illuminating something about the structure of existence that applies at every scale. The same patterns that describe the life of a black hole describe things that are much closer to us, not in the same numbers, not in the same units, but in the same shapes. And shapes matter. The shape we have been following is this: something begins. It begins with intensity, with violence, with a concentration of energy that is unsustainable, and then it settles. It finds its form, and in that form it persists for as long as its structure allows, radiating what it has, slowly, patiently, almost imperceptibly, giving back to the universe around it what it accumulated in the beginning. And then, at the end, a release. A final burst, or a final fading, or a final giving back of everything that was held. And then quiet. This shape is the shape of a life lived fully, not necessarily a long life by human standards, but a life that follows the arc, that takes the intensity of its beginning and converts it into the patience of its middle, that holds its form through all the changes in the environment around you, that gives steadily and continuously even when the giving is barely perceptible, and that, at the end, releases what it held and becomes quiet and simple and still. The black hole does this over 10 to the 67 years. We do it over decades. The timescales are incomparably different. But the shape is the same. The physics are the same. Something that has mass in the broadest possible sense, that has structure, that maintains a form, will give back over time what it held. The second law of thermodynamics does not discriminate by size or by duration. Everything that holds a form is engaged at some level in the same transaction with the universe that the black hole is engaged in. The same direction of change applies. The same destination awaits. The same arc describes the journey. And there is comfort in that. Not the comfort of knowing the destination, which is, in the most literal physical sense, the same for everything. Equilibrium, uniformity, the dissolution of structure. That is not a comfortable destination to contemplate in the abstract, but the comfort of knowing the arc, the comfort of recognizing that the patience in the middle is not a departure from the story. It is the story. The long, quiet, barely perceptible giving back, the continuous radiation of what we have, the day after day of being what we are, is the bulk of the arc. It is not a gap between the intense beginning and the eventual end. It is where most of the transformation happens. It is where most of the giving back occurs. It is where most of the contribution is made. The black hole, over its 10 to the 67-year life, emits almost all of its Hawking radiation in the long, quiet middle. The final burst is dramatic, but 99% of the mass is gone before the final burst. The final burst is the last 1%. The long quiet was where the work was done, and in the long quiet the work was not visible. It was not dramatic. It was not even detectable in any practical sense, but it was real. Every quantum emitted in the long, quiet middle was as real as every quantum emitted in the final burst. The invisible work is the majority of the work. The patient middle is where most of the giving back happens. This seems important to say clearly because we live in a world that tends to value the intense moments, the beginnings and the endings, and to undervalue the long, quiet middles. The starts and the finishes get the attention. The patient, consistent, barely perceptible middle gets overlooked. The beginning of a project is exciting. The completion of a project is celebrated. But the long middle, where most of the work is done, where the project is sustained day after day through conditions that change and difficulties that accumulate, is the part that receives the least recognition and the most doubt. The black hole gives us a different perspective. In the universe's accounting, the long, quiet middle is not less real than the intense beginning or the dramatic end. It is more substantial. It is where more happens. The universe does not discount the barely perceptible. It counts every quantum. It records every emission. The long, quiet middle is not a period of waiting for the real story to resume. It is the real story, most of it, by far. There is also something in the final burst that is worth sitting with from this closer, more personal perspective. The final burst of a black hole is the most dramatic reversal in its biography. The coldest thing becomes the hottest. The darkest becomes the brightest. After 10 to the 67 years of almost perfect invisibility, a flash that outshines everything. The contrast is absolute. The reversal is total. What does it mean that the most intense moment in the biography is the last one? That the most concentrated release of energy comes after the longest period of restraint? That the culmination is so much brighter than anything that preceded it that the preceding period seems, in retrospect, to have been building toward this? I think it means that culminations are real, that the arc, followed all the way through, has a resolution that is proportional to the patience that preceded it. Not because the universe rewards patience in any moral sense. The universe has no morality, but because the physics of the process is such that patience and intensity are not opposites. Patience is stored intensity. The energy held in the mass of the black hole during the long, quiet middle is the same energy that is released in the final burst. The restraint was not a permanent state. It was a temporary one. The intensity was not gone. It was held in the geometry of the spacetime, in the mass, in the form of the thing itself. And at the end, it was released. This is a pattern that appears in human experience too, though I offer it gently and without insisting. The things that are held with patience, the things maintained through the long, undramatic middle, have a way of resolving, eventually, with a completeness that is proportional to the holding. Not always, not inevitably. Life is not so reliable in its mathematics as physics, but the pattern exists. Patience can be a form of accumulation. Restraint can be a form of storage. And the release, when it comes, can be more complete for having been held longer. The black hole holds its mass for 10 to the 67 years and releases it in the final second. That is the extreme. The universe's most patient process followed by the universe's most complete release. We need not match that scale. We cannot. But we can recognize the shape. And recognizing the shape, knowing that patience and release are not opposites but phases, knowing that the long, quiet middle is not a gap in the story but its substance, knowing that the arc followed all the way through resolves can make the middle feel different, less like waiting, more like being. The black hole in its long, quiet middle is not waiting. It is being what it is, a sealed geometry in space, radiating at a temperature barely above zero, maintaining its form through the changes of the universe around it, not waiting for something to happen, simply being with perfect consistency what the collapse created. And that being, that patient, consistent, barely perceptible being, is the bulk of its contribution to the universe. The mass that was accumulated in the violent beginning is steadily, quietly, continuously being returned. The giving back is happening, every moment, at a rate too slow to measure, but happening. You are also, in your own way, giving back to the people around you, to the time you inhabit, to the particular moment in cosmic history that you are a part of, not at the scale of a black hole, not over 10 to the 67 years, but in your own arc, with your own intensity at the beginning, your own patience in the middle, your own eventual release of everything you hold. The pattern is the same. The shape is the same. And the universe, in its perfect and indiscriminate accounting, records every quantum of it, every moment of it. Every act of giving back, however small and however invisible, is real. It counts. It changes the state of things. It is part of the thermal history of this particular corner of the cosmos. That is what the slow death of black holes tells us about ourselves. We are also structures that hold and release. We are also arcs that move from intensity to patience to completion. We are also part of the universe's transaction with itself, gathering and giving back, accumulating and dissolving, maintaining form through change, and then releasing that form when the time comes. Not on cosmic timescales, but on human ones. And the human timescale is from the inside just as real and just as complete as the cosmic one. Rest in that. The arc is real. The patient middle matters. The release will be complete. And the universe holds the record of everything. We are almost at the end of the journey. Let us spend a little more time here in this space between the physics and the personal before we close. Because there are a few more threads worth drawing together. A few more things the story of the black hole's slow death illuminates that we have not yet said directly. One of them is about the nature of endings themselves. We have a complicated relationship with endings. They tend to carry in human experience a weight of loss, of finality, of something that was becoming something that no longer is. We mark them with grief and with ceremony. We build rituals around them. We resist them sometimes. We fear them often. The ending of anything we value, a relationship, a project, a life, an era, carries with it the sense that something real has been removed from the world, that a presence has become an absence, that a something has become a nothing. The story of the black hole asks us to look at endings differently, not to feel less about them, but to see more in them. The black hole's ending is complete. That is the first thing. It does not end partially. It does not leave a half structure behind, a diminished version of itself that persists as a reminder of what it was. It ends all the way. The mass goes to zero in the most common scenario. The horizon shrinks to zero. The geometry relaxes to flat. The ending is as thorough as an ending can be. And this thoroughness is not a loss of something that should have remained. It is the completion of a process that was always going this way. The endpoint was written into the beginning. The evaporation was implicit in the horizon. The zero was always the destination, and nothing that was the black hole is gone. This is the second thing. The ending of the black hole is not a destruction of what it held. It is a transformation of what it held. The mass is now radiation. The information is now encoded in the correlations of that radiation. The geometry is now flat spacetime. Everything that was gathered is still in the universe, in a different form, distributed rather than concentrated, spread rather than sealed, but there. The ending did not eliminate what existed. It transformed it, changed its form, released it into the universe in a way that is, in principle, completely reversible, in the sense that the full information about what was there is encoded in the final state, even if in practice the decoding is impossible. This is the universe's way of ending things. Not destruction, transformation, not elimination, distribution, not loss, change of form. The black hole, when it ends, does not leave a hole in the universe where it used to be. It leaves the universe richer by the radiation it emitted, richer by the information encoded in that radiation, richer by the thermal history that its entire biography contributed to. The universe after the black hole is not diminished by the black hole's absence. It is informed by the black holes having been there. There is a way of thinking about endings in human experience that resembles this. Not identical, because human experience is not physics, and the analogies between the two are always approximate, but resembling. When something ends, a person, a relationship, an era, what ends is the form, the particular configuration, the sealed structure, but the effects of that form, the changes it made to the world around it, the information it contributed to the state of things, do not end. They are distributed into the world. They are encoded in the people who were changed by the thing that ended, in the works it produced, in the decisions it influenced, in the lives it shaped, in the memories it left, in all the ways the world is different for its having been there. The form ends, the effect continues, the structure dissolves, the contribution persists. Not as a monument, not as a lasting physical structure, but as information, as change, as the difference between the world that is and the world that would have been without it. The universe's accounting applies here too. Nothing is truly lost. Everything is transformed. This is not offered as a consolation that makes endings painless. Endings are painful. The loss of form is real. The absence of presence is real. The grief is appropriate to what is gone. But alongside the grief, and not in contradiction of it, there can be this: the knowledge that what was there left its mark, that the world is different for it, that the transformation was real and is permanent, that the contribution is encoded in the universe's state in ways that cannot be undone. The black hole, when it finally evaporates, does not leave the universe as it found it. The universe is permanently changed by the black hole's presence, and the universe will carry that change forward, encoded in its thermal history for the rest of its existence, which is to say, forever. That is a form of permanence, not the permanence of the structure, the permanence of the effect, not the black hole forever, but the mark of the black hole forever. The contribution forever. The universe, changed by the presence, forever. Let us also sit with something that we mentioned briefly at the very beginning and that has been implicit throughout. The story of the black hole is a story about the meeting of two great theories, general relativity and quantum mechanics. And that meeting, that collision at the event horizon, is one of the most productive collisions in the history of physics. It produced Hawking radiation. It produced black hole thermodynamics. It produced the Bekenstein entropy. It produced the information paradox. It produced the holographic principle. It produced the whole field of research into quantum gravity that is still ongoing today, string theory, loop quantum gravity, and all the other approaches that are trying to find the theory that unifies the two great frameworks. Black holes, in dying, gave physics some of its deepest questions, and those questions are still being worked on. The slow death of black holes has been a slow birth of ideas. Every attempt to understand how the black hole evaporates, how the information escapes, what happens at the singularity, what the Planck scale physics looks like, has pushed the boundaries of theoretical physics further. The questions raised by Hawking radiation are among the most generative questions in modern physics. They have kept physicists busy for 50 years and will keep them busy for as long as physics is practiced. There is something beautiful in that. The black hole, the most sealed, the most private, the most absolutely contained structure in the universe, has, in its dying, generated more openness, more questions, more productive uncertainty than almost any other object of study. The thing that was most closed has opened physics up. The thing that held everything has released ideas that have spread across the entire field. The paradox at the horizon has been the engine of inquiry for half a century. The black hole, in evaporating, has given physics more than it took. That is also a pattern worth recognizing. The things that are most resistant to easy understanding, the things that most completely refuse to yield their secrets quickly, the things that present the sharpest apparent contradictions, are often the most generative. The information paradox is not resolved, but the attempts to resolve it have produced some of the most profound advances in theoretical physics of the last 30 years. The black hole, in dying so slowly and so mysteriously, has been the most patient teacher physics has ever had, and physics is still learning from it. That patience of the problem, the willingness of the universe to hold a question open for 50 years or more without resolving it cleanly, is itself a lesson. Not everything resolves quickly. Not every apparent contradiction finds its resolution in the first decade of inquiry. Some questions are so deep that they require the development of entirely new mathematics, entirely new conceptual frameworks, entirely new ways of thinking about space and time and information. The black hole is one of those questions, and the physics community, to its credit, has not given up, has not declared the question too hard or too obscure to be worth pursuing, has continued, patiently, decade after decade, to push at the edges of what is understood. There is a patience there that mirrors the patience of the black hole itself. Intense beginning in Hawking's 1974 paper, long, productive middle in decades of work by hundreds of physicists, resolution, hopefully, still in the future, but the arc is there, the direction is there, the progress is real even when it is slow. Let that settle into the quiet of the room you are in. The universe poses questions with extraordinary patience. Physics answers them with extraordinary patience. And the questions that resist the quickest answers are often the ones whose answers matter most. The black hole will eventually evaporate completely. The information paradox will eventually be resolved completely. Both are, in their different ways, the same story. Long patience, steady approach, and eventually completion. You are surrounded tonight by a universe that has been asking and answering its questions for 14 billion years and will continue for timescales we cannot name. You are a part of that process, a brief but real part, a contributing part. Your particular form, your particular configuration of atoms and chemistry and consciousness, is one of the universe's answers to one of its questions. What forms can emerge from the conditions of a stelliferous era on a rocky planet near a medium-sized star? You are part of that answer, brief, specific, real. And when your form eventually dissolves, as every form dissolves, the information you contributed to the state of the world will persist, not in a form you would recognize, not in a way you could read back, but encoded in the people you changed, in the choices you influenced, in the ideas you carried forward, in the warmth you gave to the people near you, all of it permanently part of the universe's state. The black hole gives back everything. So in the end does everything. So in the end do we. Not because we choose to, though choosing to matters enormously in the human scale of things, but because the universe's accounting is perfect, and nothing that happens leaves the universe unchanged. You are already, in the deepest physical sense, giving back. Every breath is an exchange with the atmosphere. Every thought is a change in the state of the matter in your brain. Every act is a ripple in the web of causes and effects that stretches forward through time. You are already always part of the transaction. Rest in that knowledge. The transaction is already happening. The giving back is already underway. The arc is already following its course. And the universe, patient, vast, remembering everything, is already receiving it all. That is not a small thing. That is everything. We have come a long way tonight. From the collapse of a massive star, to the birth of an event horizon, to the quantum vacuum seething at the boundary, to the temperature barely above absolute zero, to the incomprehensible timescales of the long evaporation, to the final burst, to the question of what remains, to the dark and quiet universe that follows, and finally back to here, to this room, to this moment, to this particular place in the story. Let us take a few minutes to let it all settle. Not to summarize it, not to reduce it to a list of things learned, but to let the whole arc rest in the mind the way a long piece of music rests in the body after the last note has sounded. Not gone, not analyzed, just present, still resonating, still doing something. What does the story of the black hole's slow death leave you with? For some people, it leaves a sense of perspective. The troubles and urgencies of the day, the things that felt pressing before this conversation began, may feel slightly differently sized now, not dismissed, not minimized, but set inside a larger frame. A frame in which the most powerful structures in the universe dissolve over timescales of 10 to the 94 years, in which the stars burn for trillions and the atoms hold on for even longer and then let go, in which the universe itself has a direction and an end and a final state, and in which our particular moment is both infinitesimally small and completely, thoroughly real. For some people, it leaves a sense of connection. The atoms that make up your body were forged in stars that exploded billions of years ago. The carbon, the oxygen, the iron, the calcium, all of it was produced in the nuclear furnaces of stars that lived and died before our sun existed, scattered by supernova into the clouds from which our solar system eventually formed, gathered into planets, dissolved into chemistry, assembled by 4 billion years of biological evolution into the particular arrangement that is reading these words tonight. You are, in the most literal physical sense, made of star material, and the star material came from a universe that has been evolving since the Big Bang, a universe that will continue evolving long after every star has gone out, a universe of which you are, for this brief moment, a part. For some people, the story leaves a sense of the value of patience. The black hole's long middle, the 10 to the 67 years of barely perceptible radiation, the continuous, invisible giving back, is the majority of the arc. Not the intense beginning, not the dramatic final burst. The long, quiet, consistent middle, the patient being of what it is. That is where most of the transformation happens. That is where the work is done. In the long middle that no one watches, that no instrument can measure, that seems from the outside like nothing is happening, the something is happening. Quantum by quantum, moment by moment, without fanfare, without recognition, but happening. For some people, the story leaves a sense of the completeness of endings. The black hole ends completely. It does not leave a residue of itself, a diminished version that persists as a reminder of what it was. It gives everything back. And in that total giving back, in that thorough completion, there is something that resembles integrity, a following through, a finishing of what was started, a transaction completed all the way to zero. And everything that was the black hole, every quantum of mass it held, is now in the universe, changed in form, but there. For some people, it leaves wonder. Pure, simple, irreducible wonder at the strangeness and richness of the universe. that a region of spacetime sealed by its own geometry can have a temperature. That empty space is not empty but seething with virtual pairs. That information, the pattern of the thing, is preserved even when the thing is gone. That two of the greatest intellectual achievements in human history, general relativity and quantum mechanics, meet precisely at the event horizon of a black hole. And when they meet, they produce a glow so faint that no instrument can measure it, but so theoretically certain that it changed everything we thought we knew about the permanence of the universe. That is wonderful, in the oldest sense of the word, full of wonder, deserving of it. And for some people, perhaps, the story leaves a quietness, a settling, a sense that the universe is doing what it does, following its laws, working through its processes, patient and vast and indifferent in its mechanics but extraordinary in its results, and that being a part of it, even briefly, even as an arrangement of atoms on a small planet in an ordinary galaxy, is not nothing, is in fact something remarkable. The universe has produced, in you, a configuration of matter that can ask what happens to black holes when they die. That can follow the argument through the physics and the timescales and the information paradox and arrive at the end at a feeling of having understood something. Not everything, but something. And that something is real. It is a change in the state of a mind. And the state of a mind is the state of matter. And the state of matter is part of the state of the universe. And the universe, as we said, keeps perfect accounts. You understood something tonight. That is now part of the universe's history. Permanently, unchangeably, the understanding happened. And because it happened, the universe is different than it would have been without it, by a very small amount, by an amount that no instrument will ever measure, but by an amount that is real. The physical state of this small corner of the cosmos has been altered slightly by the fact that tonight in this room, a mind followed the story of the black hole's slow death and arrived somewhere it had not been before. That is not nothing. In the universe's accounting, nothing is nothing. Everything changes the state of things. Everything counts. Every quantum of Hawking radiation counts. Every breath counts. Every thought counts. Not in a grand, cosmic, destiny-laden sense, but in the simple, physical, thermodynamic sense that everything that happens leaves a mark, changes the state, contributes to the history, and is, in the deepest possible sense, permanent. The black hole is patient. The universe is patient. You can be patient too. Not in the way that the black hole is patient. 10 to the 67 years of cold, dark persistence, but in the human way, which is its own kind of remarkable. The patience to let difficult things take the time they need. The patience to sustain the long middle when the beginning's intensity has faded and the ending is not yet in sight. The patience to keep giving back to the people around you, to the time you inhabit, to the particular corner of the universe that you are responsible for, even when the giving back is barely perceptible and no one is measuring it. The universe measures it, not with intention, not with care, but with perfect completeness. Every act of giving back is encoded in the state of things. Nothing is overlooked. Nothing is too small to count. The quantum that the black hole emits in the coldest, darkest, most isolated moment of its long evaporation is as real as the quantum emitted in the final burst. The barely perceptible is still perceptible to the universe's perfect accounting. So close your eyes now if you have not already. Let the breath slow to whatever pace it finds on its own. Let the images of the evening drift. The collapsing star, the event horizon, the glowing quantum vacuum, the barely perceptible temperature, the trillions and trillions of years, the final burst, the quiet universe, the radiation spreading outward carrying the record of everything. Let those images drift and settle and become less distinct. You do not need to hold them precisely. They will be there when you return to them. The universe will also be there, patient and vast and following its laws while you rest. The black hole is still out there. Many of them, many sizes, all stages of their incomprehensible lives. The nearest stellar black holes, a few thousand light years away, are barely into the first fraction of their first fraction of a percent of their evaporation timescale. The supermassive black hole at the center of our galaxy, Sagittarius A with its 4 million solar masses, is even more patiently waiting, colder than anything, barely radiating, holding its form in the dark center of the galaxy that contains us. All of them are doing what they do, holding their geometry, radiating their barely perceptible temperatures, existing with perfect consistency in the shapes that the collapse created, patient beyond any concept of patience. And you are here in this room, on this planet, in this galaxy, in this universe, for this moment of cosmic time, briefly and completely and really. The arc of your existence is its own thing, with its own beginning and its own long middle and its own eventual completion. Different from the black hole's arc in every particular, but shaped by the same laws, proceeding in the same direction, contributing to the same cosmic history, part of the same transaction. The universe is vast, you are small. Both of those things are true simultaneously, and neither one cancels the other. The vastness does not diminish the smallness. The smallness does not diminish the vastness. They coexist. They are both real. You are a small part of something incomprehensibly large, and you are contributing to its state, and the universe is keeping the record, and nothing is being lost. That is perhaps enough to rest with. The universe is patient. The arc is real. The record is perfect, and you can sleep now. The black holes will still be there when you wake, holding their geometry, barely radiating, patient as ever. The universe will still be expanding. The quantum vacuum will still be fluctuating at every horizon. The laws of physics will still be applying themselves without exception and without preference to everything that exists. Everything will be continuing exactly as it was, and you will have rested. And resting is itself a kind of giving back, the body recovering, the mind settling. The particular arrangement of atoms that is you, maintaining its form through one more night, ready for whatever comes next in your own arc. Resting is not absence from the universe. It is participation in the universe at its quietest register, the register that most resembles the black hole at the coldest point of its long life, barely perceptible, almost still, but present and real, and radiating in its way whatever quiet warmth a resting body radiates into the room around it. Let that be enough for tonight. The story is told, the arc is followed, the universe is patient. Rest now. Everything else can wait.